Because I think you have many presentations. I think we should stick as much as possible to testimonials as if we start with the habit to accumulate a lot of delays, then tomorrow we have three witnesses, so like tomorrow the whole thing will take. So I'd like to try to
Okay, just here.
Very good. We're just starting in a minute. Take your seat. There's also coffee and snacks. Come for you later. You have the program
Just 1 minute, please. Hello, everybody. Whoever is presenting this afternoon, if you could actually bring your presentations to the laptop now and we save some time later, it would be great. Thank you.
Yeah, I think that will be announced. Don't forget to do this.
There's another one? we have to say this is always
of live streaming to a YouTube channel our beautiful workshop here. And I would like to ask you if anyone objects against this idea of streaming it. You have to raise your hand because then it's not going to happen. So only if all agree we're going to have the live stream and the recording, then it's going to happen. So may I ask you, is there anyone who would like to object against this? There's one. You told you're on TV this tonight. So no objection, then please, yeah, you can. Okay, a very warm welcome to our first SENSECO joint workshop. So I'm Martin, for those who haven't met me yet. Together with Jochen, we are chairing this cost action, and I would first like to thank for all of you for coming. Of course. I know there are a lot of other things happening all around the year, a lot of conferences we can't expect. I want to travel that long way, but I'm really grateful, or we are really grateful you did so, and so thanks for that. I'd also like to welcome all the new participants. I think, if I'm not mistaken, Jochen just gave me the last numbers. About 40 people have joined more or less after our first MC meeting in Brussels. So I think this is a fantastic number, so welcome, and thanks for coming too. And then I would like to thank already the working group leaders and co-leaders for putting up this excellent program that we have. So I think this is really the meat of such an action, the working groups, and yeah, I think you put a nice program together, a nice mixture of revisiting our objectives that have been defined in the proposal, and they're listed in the MOU and so on, plus showing results, showing the activities of the first term period, showing some results, plus some research presented, related research to your working group content. So I think that's a very nice setup. And then I would like to finally thank also our local host, Bruna, I think, who did an excellent job organizing it very smoothly, so it's fantastic. I just want to do a very few introductory slides. That we're having a program here, and so the idea is to start at 3 with the working group 1 today, running until 6. I already heard there's an extra talk, so maybe run a bit longer than 6 p.m. But I hope they can sort of try to squeeze that in, because I need to talk to the core group half an hour. So the core group are the people who are more sort of managing, and we got to prepare for the Wednesday MC2. We got to clarify a few things. So yeah, so core group, please don't run away at 6, and we meet here very briefly. Okay, then we have the very long Tuesday. That will be hard, because we have the working group 2 in the morning. Then we have lunch in the here in the university. I believe Bruna will maybe guide us there or tell us something. And then we have the working group 3 in the afternoon, and then the working group 4 also. So that would be a very long day. And then we have the the dinner afterwards, and then here on Wednesday we have the management committee meeting, which is only for embassy members and substitutes. So everyone who's not a member or substitute representing one of the member countries is free on Wednesday. Yeah, you don't have to stay. You can do something else, or maybe you already know and you planned your trip back. Okay, then we have so during the first meeting in Brussels in October last year, this governance structure was approved. So you probably, most of the people who are in a certain working group already know who are the responsible leader or vice leader, but I'm just listing in case you maybe also get interested in other working groups. Then you see who is your basically your contact point here. For the grant holder, you won't love it, but I just also want to mention that Joachim is our science representative. He's basically the link between the management committee and the grant holder, which is the grant holder institution is Valencia. So he's the link, very important link. And then very important is Beatrice, who's also here today, who's going to manage and handle your claims, your trouble claims. So. Then I want to point you also to the fact that there are a couple of key documents and websites. So we have the cost website for SENSECO. There you can see how many member countries we already have. You can see the memorandum of understanding, which is the working basis for this whole action. There are all the objectives, tasks, deliverables already listed there. So you can also, it's the responsibility of the management committee to check that we are not, to monitor that we are going in the right direction. So I think this is an important MOU, but also on the general cost website you find the so-called Vademecum, which is the rule book. All rules are listed there. For instance, what costs are eligible for the reimbursement. That's one thing, all the details are there, but all the other things. And there are many other guidelines on the management, communication, reporting, etc. And then we have our beautiful SENSECO website that was kindly set up by our list communication group together with Miriam, who put all the content. It should be managed now by our science communication managers, but they couldn't make it here unfortunately. So we could see what we're doing there. Anyway, you find there all information about new meetings, new short-term scientific missions, training schools, etc. And you'll be able also, but we still have to discuss how we're exactly doing that, you will be able to access the minutes of the meetings, of different meetings. Maybe you couldn't attend a meeting, but we want to make it very transparent that all decisions that we take in the meetings are available. And the presentations, let's say more presentations, or we have to see presentations and workshops. Okay. So I just want to briefly summarize what we can actually do in the cost activity. So we have, per year, we have a sum of about 110 to 130k euro for activities. And with these activities, we can do short-term scientific missions, we can run training schools, we can hold workshop like this workshop today, attend conferences. Plus, we have the funds for the action manager that has to come on top of that, which is normally 15% on top of this lump sum here. So this is all the money, of course, for networking tools. We can't fund any research. Yeah. So the research has to come from projects, PhD projects, postdoc projects, whatever projects you're anyway doing. Yeah. So research itself cannot be funded, only the network. And in principle, it works like that. That with the objectives, also the tasks and the deliverables, like meetings, training schools, have already been predefined in the MOU. But in the management committee meeting, then we are together defining where it's going to happen, when it's going to happen, who's going to host it, etc. So these things need all to be discussed and approved during the management committee meeting on Wednesday. Okay, just want to update you. So on the proposal, we had 27 member countries, and action start we had 30, and now we already have 33, and the maximum being 37 plus 1, Israel. We are already coming close to the maximum possible number of member states. And so this is important also because it's also very much driving the amount of allocated funds that we can spend. And what we're currently missing, I think, is only Albania, Lithuania, Montenegro, Macedonia, and Slovenia. So if you have contacts in these countries and you think there are researchers who could be interested who would contribute to this action from these countries, please let me know, and then we can maybe contact them and try to find members also from these countries. Cost policy, excellence and inclusiveness, I just want to mention that these are, so cost office will very much judge us not only by what we are doing in terms of have we done the task that we promised, have we delivered the deliverables that we promised, but also cost policy excellence and so on. And so it's important to have a good number of ITC countries. It's good, we should have a good gender balance, and we should have many early career investigators. I think on all, I don't have the actual numbers now, I'm going to have them next time, but in all of these three categories I think we're doing pretty well. So I think that also if you look around, you can see many young people, good gender balance and so on, good variety of countries. Okay, I'm going to skip this one. So I just want to, I mean, now for each working group we have objectives, tasks, milestones and deliverables. I just wanted to, I think you will learn them in more detail than in the working group workshops. I just want to run quickly over it, that you see like, okay, we have in blue we have the objectives, then in green we have tasks and milestones, which is basically the same, and in red we have deliverables. So you see in working group 1, they are looking at scalable traits, they are looking on the spatial scaling aspects, they're using radiative transfer models and so on in their objectives. And then how they are doing this, training schools, STSM, workshops, etc. And here you can see what they promised, data set and protocols. Right. In the next working group, they are concerned with the time aspect. So they're looking on time series and the scaling in the time domain, time series modeling, etc. And they have also working shops, training schools, intercomparison exercise and so on, and as deliverables, protocols, data sets and papers. And in the working group 3, that's about multi-sensor fusion and multi-sensor synergy, also using partly RTMs and with an application more on crop, water and nutrients and stress. So here workshops, training, school, domain and protocols and guidelines as an output. And in working group 4, that's dealing with radiometric measurements and how to make them traceable to establish traceability chain and how to do an uncertainty analysis. And workshops, training, school, software, in this case 2 papers as an output, and so on. So this is just a broad overview to maybe refresh or to make you aware very briefly what the working groups are dealing with. We also have 2 all working groups activities planned, like an overall training school and a conference session at the end. Okay, that's enough for that, and just want to point you to a few things that are often forgotten. So the cost reimbursement, please, you have, in order to be eligible for reimbursement, you have to sign the attendance list, very important. So if you don't sign the attendance list, you don't get your money, yeah, that's very important. So we should have, do we have attendance lists actually? Have people already put their, I will pass it. You pass it through, huh? Yeah, okay, very important. So every day, yeah, not just today, but you've got to sign it today and you've got to sign it tomorrow. And if you are attending the MC meeting on Wednesday, you've got to sign it on Wednesday. Otherwise, no money. They're very strict. Even if you forget to put the signature, we can't send you the form and have you sign later on. Cost will refuse it. They're very strict in that. So please sign every day you're attending. Please sign the sheet. And then another thing, client submission. So when you come back from this trip, you have 30 days maximum to submit your claim. However, that brings us in a difficult situation because the end of this grant period is 30th of April. And so please try to do it within 7 days. Yeah, because we have forecasted a budget number for this Aveiro workshop and MC meeting, but we will just know when all the claims have arrived what we were really spending, and in case we are underspending, we would like to spend this money, if possible, for another purpose. Because what we don't spend is gone. Well, what we haven't spent by the 30th of April is gone. We can't take it into the next year. So that's why I'd like to ask you to please, within 7 days, put your claim, so then Beatrice has everything together, and then we can still see what we're doing, of course, via an e-vote and MC, to the MC, what we propose to do with the remaining funds. Okay, and then just things that very quickly only, okay, for your claiming of your travel cost, you have to submit your ticket. That's very important. If you travel by car, partly, you need a Google Maps thing here that shows the distance, because that will be the basis for the reimbursement, flat against kilometers. And for train, bus and ferry also you need to submit your ticket. Now for accommodation,
When you say submit the ticket, it can be online or it has to be the original by its office.
now you got to keep the ticket indeed. You got to keep the ticket on, I think you have to scan it or something.
It's
and
online.
digital, yeah, digital. You scan it and then you put it as a letter. So for accommodation, for the hotel, you don't have to submit your hotel receipt. It's not needed. Yeah, you get a flat of 120, and what your hotel costs, whether that's 20 or 200, it doesn't matter. You only get 120. Yeah, no receipt needed. And for the meals is the same. So per day you get 2 meals, so 2 times 20, unless you're officially invited by something, but we don't have an official dinner here. And you don't have to keep a receipt of your meals, you get a flat rate of 20. And the local transport, unless when it's less than 25 euro, you don't need the receipts. Yeah? You just say, I was coming, I used the train for €8.50 and you can claim that. You don't need the receipt. Only when it's above 25 euro, your local transport. Was it actually per day or for the whole trip? Per day? Okay, I think we have to check that once more.
I think it's per trip.
For the trip? Per trip?
Yeah.
Per trip? Okay, per trip. So if you have more than 25 euro local transport per trip, you have to, all receipts are required. And a taxi you can only use after 10 p.m. and before 7 a.m. And it can't be more than 80 euro. So, yeah, I think these are the most important rules. And that's already from my side. Bruna, do you wish to say something regarding dinner or anything with local logistics?
Yes. Thanks. So just a couple of things. I will pass 2 lists. One is the attendance list, and the other one is for the dinner tomorrow. I need to know who is joining the dinner, if you want vegetarian, and if you have food allergies. Just fill in, all the names are here. Then I received some requests for the bus on Wednesday, and I have a list there on the desk of those who sent me an email. Please confirm if your name is there, in the case you sent, otherwise obviously not there. For the lunch tomorrow, we will have it in the, well, tomorrow and on Wednesday for those who want to stay. At the university restaurant, which is just 2 buildings across nearby. I think that's it for now. If you have any questions, just let me know. We have some extra plugs in the bag, so if you need. And if you have any questions, just let me know. Okay? Yes.
What's the Wi-Fi password?
Yeah. The Wi-Fi isn't working. I requested a special password for those who don't have Chrome, and it's not working, and I'm trying to fix it, and I will go there now to press a little bit more. Yeah. More questions for now? No?
Okay, thank you. then I'm handing over immediately to the working group 1. Cheers, and please. We're sorry guys, 15 minutes late.
So good afternoon everyone, thank you very much for being here, and thank you to Runa for organizing the workshop. What we are going to present now is just briefly what are the main objectives of working with one. So as you can see that the main focus is scaling up different biophysical parameters from the leaf level. I have a slide here. Sorry. From the leaf level to satellite. And the working group is mainly divided into 3 main blocks. So one will be leaf dynamics, the next one will be the scaling up protocols, and finally the Lichens transfer models. This is what we present. So as you can see, there is like a pretty ambitious objective because we're going to tackle 3 different topics, and that's why we decided to create a team to achieve that. In the leaf level, it's Sari and myself who are going to be like more active in that topic than for the scaling map protocol. So me, Paula from Portugal, and Javi. So I'm from the University of Valencia, and then Paula from Portugal, and Javi.
Working at the Biomass Distribution in Germany. Here also, I think, Sari is officially here.
Sari is not here, she's in Finland. She just moved there for a scholarship. And then for the Multispectral Camera model, we have Johan leading that section together with Svina. Going a little more into the different objectives, so the first one will be to identify which are the main leaf and top of canopy biophysical and biochemical traits. And to do that, what we would like to do is ask this question like, what are the main biophysical molecular traits at this level that are needed to be able to improve our estimation of photosynthesis, and then how it is accurate that we have to make sure that different scales, and also to extrapolate that to satellite level. We aim to do that by doing different short-term missions, scientific missions, and summer schools. That is why we encourage the presenters of working with one to highlight which topics they are working and which short-term mission they can propose so we can achieve this objective. And then we would like to have workshops to be able to discuss these points and then improve our deliverables and also communicate. The next objective will be delivering or working in different protocols to do this scaling up. And then mainly we would like to do that through the workshop and summer school. And then finally, regarding the Lichens model, Jochen already organized a workshop with Bruno, where they tackle the main experts working with different Lichens models and mainly focus on fluorescence. And they will do a random experiment in that direction. He will now present a little bit the main output of this workshop and also what are the next steps. I will not go too much into detail here. And also as a first step of working with one, and to be able to connect, because we think that we have like 2 main groups, one that are doing the field experiments, taking the measurements, and then we have the modelers. So we prepare a first questionnaire where we mean to address all these main 2 groups to know which are they working, which are the points that are missing, and then being able to tackle that through this working group.
Yeah. So we had originally actually planned to set you up all and basically ask you to do the questionnaire like in 15 minutes during this meeting, but we have these problems with the internet, and also our session today is quite packed with a lot of presentations. But we are going to send around again, because already sent the link to this questionnaire, and I would like to ask you to do this questionnaire during this meeting. So after every coffee break, at the beginning of each session, we are going to try to count the number of people who in the last hours did the questionnaire, and we would like to have you all doing this questionnaire during this meeting, because the original plan. And yeah, please do it. Maybe otherwise you will not be reimbursed. But
That could be a good one.
good questions. But yeah, Valencia, of course. So, but just please do it, because for us it's valuable information to try to understand what the community or the community that is gathered here is doing. And based on the results of this question, we would like to actually develop new activities and try to focus on the things that are the weak points we detect, or try to reinforce this lack of knowledge. So for us it's important to plan the next activities in the next year and the following years. So we are going to push you to do this questionnaire during this meeting. Thank you very much.
So now the presentations. We'll have a lot of presentations, so we would ask you please to keep on time, because we are already a little bit delayed. We will warn you when you reach to the 10 minutes, okay? So presentations are 15 minutes plus 5 for questions. So we will see our sign saying 10 minutes. And then remember that you should finish it on time, and then we'll have 5 minutes more or less for questions, okay?
So now we will have Johan and Alberto, and actually they are going to talk about this intercomparison of the different transfer models for the simulation of sun-induced fluorescence. And they are going to present a bit the outcomes of the meeting in Brno and their activities.
Okay, good morning everyone. So regarding working group 1, now we have a presentation more about the modeling approach of how to tackle the scaling problem. This presentation is given by me, but I did this work, and I'm doing this work together with several other colleagues. Alberto is here, but we also have some people all the way to Australia. There's all the way from Tunis. Abdelaziz also here, he's giving a presentation after me. And basically we try to involve the whole community on also implementing scaling issues by means of relative transfer models. So everybody is a bit aware, I guess, of the scaling issue, and we measure at various scales of our vegetation, so the reaction centers in the photosystems, these into the leaf pigments, a canopy, this you can have over landscape level and so on. We also have different instruments where we measure all these scales. And this also brings us a little bit to the objectives of our working group. And particularly I'm interested in tackling two objectives. The first one is to identify scalable leaf to canopy biophysical and biochemical traits. So I would like to propose an approach how we can do this scaling from leaf up to our satellite scale. And then objective 1.3 is about to provide a theoretical scaling assessment by means of these physical models, these relative transfer models. And here this I do together with Alberto. And we want to also to propose an approach how we can compare several models. And we had already actually a workshop done in Brno last month, where we started identifying the key problems and also the state of the art of the different models. So physical models, there is a tendency that more and more also they include photosynthesis and photochemistry into them. These are the key models, but various more models have been identified. And then questions arise how they are, if they are consistent, are they all used for biochemistry measurement, and can we use them for scaling approaches? So we brought all these people together on this meeting, and we discussed how is the way forward in using these models. Maybe a quick overview on these models at the leaf and canopy scale. You can imagine that we have these models, they have a long history, and they are in all kinds of complexity for all kinds of purposes. So you see this for the leaf, but also for the canopy, that more and more they became more complex. But if we see to the trends at the leaf and then also for the canopy models, maybe more during the 90s and the 2000s, they include more variables to try to have all the pigments included. But actually there was a shift since the 2010 or so, especially pushed by Fluorescence project. It's not just think about the pigments, but also have photochemistry into these leaf models. No? So basically since the last 8 years, since 2010, many of these leaf models, they have also biochemistry models into the leaf models implemented. Afterwards, there will be a talk on a ray tracing approach by Abdelaziz Gazel for having a fluorescence and output on leaf and canopy model. And the same trend we see also at the canopy scale. So before there were a lot of efforts being done how to make them more realistic, more structure, more variability. But this was more or less until 2010 or so. And for the last 8 years, actually, the trend is more into not just being more realistic, but also have photochemistry and the whole photosynthesis process into the models. And this was especially initiated by the scope model. But after the scope model, all the other main canopy models also have included the same approach, so that you have your structure, but at the same time, on the other hand, you also have fluorescence and the whole photosynthesis apparatus into these models. So this was a little bit the outcome of the meeting that we had. We brought all the key modelers together in one room, and everybody was talking about the latest status and the latest progress and how we can compare these different models. And everybody showed also willingness to continue with it. And now in this meeting, we would like to also, let's say, define like a baseline for how to start with the comparison study. Alberto will later on talk more about it. But when we have both these leaf models and canopy models, we also identified that leaf models are very diverse. On one hand, you have all the models based on prospects or very simple layers. But on the other hand, you have also completely different approaches, more plant physiology or ray tracing. So it's very difficult to compare one leaf model against another leaf model. So for that reason, at the leaf scale, we plan to start with sensitivity analysis, global sensitivity analysis, where you identify the drivers. So what are the most important variables for fluorescence outputs? I think that's a good starting point to know if these models are comparable anyway, right? So do they provide the same sensitivity, the same variables, drive fluorescence? On the other hand, the canopy models, and later Alberto will talk more about it, they are pretty much the same, that they all need this leaf input, then they have their structure, the scattering processes and so on. And so they are more easier comparable. They all have more or less the same variables. So now I will give the floor to Alberto, and he will present how we will compare.
Yep. Well, the main goal, the first idea that came to our mind when we go for a model intercomparison was to document the variability between the different fluorescent radiative transfer modeling in a very well-known condition. Maybe this can remind you the RAMI intercomparison, but in a different way, because we don't have an absolute reference standards for these models. The way to evaluate them is to compare them together under the same circumstances. So the objective is not only to identify which model differ to another, but also a model is not better because matched to another model. But we can identify from these differences if we are having any lack of information or missing information from some modelization. We are still in the first evaluation about how to develop the measurements and the different experiments. So tomorrow we will have a lunch between all the modelers. There, for example, for the canopy approach, following partially the solution previously agreed with the RAMI exercise, we will go for different solar angles, even considering hemispherical diffuse downwell irradiance, and also with different view angles, but instead of talking about solar domain or the purest corner, as previously done, we will go for a more realistic solution. I mean, using real data to validate, to intercompare the models. So for that, we will be varying the LAI, the leaf size, and also the leaf angle distribution. And because not all the models behave the same, we will choose two different approaches, one for homogeneous cases and another one for heterogeneous or 3D intercomparison. And for making the things a little bit easier, we will go for the same leaf level approach, let's say Prospect, But if the canopy model doesn't use this leaf model, we can provide the same inputs and the same outputs to match the differences.
Okay.
But we will go to talk about, because we are in an initial stage, so tomorrow in the lunch we will go all together to talk about that.
Thanks, Director. Okay, now maybe the second part of this talk, I would like to continue on my approach of how to tackle the scaling problem. So we all have our measurements at the leaf scale, and then the question is, how can we use leaf measurements for satellite applications? No? So how can we do the upscaling from leaf to canopy, atmosphere, and so on? And actually, maybe it can be quite easy. If we have leaf measurements, we could make use of these physical models that we just talked about for doing the whole upscaling process. And then the question is like, how can we use leaf data into canopy models? And for this, we have been developing a solution that everybody can use. It's freely downloadable and it seems to work out. So basically, what we did over the last 8 years is we collected all the leaf models and the canopy models and atmosphere models, and nowadays we can couple them very easily in this automated relative transfer model operator, ARTMO it's called. So you can couple any leaf model with any canopy model, and nowadays you can also add atmosphere models, Lichens or Motran, so you can do the whole scaling. But that's just modeling part, but more interest I think for this community is that we have our own leaf measurements. How can we make use of this framework that we have our own field measurements, making use of these physical models for upscaling our own data. So no longer simulated data, but our own data. When we look back to prospect sale, the very basis of leaf and canopy modeling, so we have our leaf models, it gives us output, reflectance, and transmittance. We have our leaf variables, this goes into a canopy model, and it does an upscaling. That's the approach with simulated data, but we can do exactly the same when we have our own leaf spectral measurements, so reflectance and transmittance. And these we all measure very easily with our leaf clip. We have reflectance data, we have transmittance data, maybe you have some pigments, chlorophyll, carotenoids, whatever. So that data you could also easily put into your canopy model, and this way you do the upscaling for certain LAIs, certain geometry, and so on. So it's very easy possible. The only thing what was missing was a tool that does this job automatically. And for this we have just developed a new module into ARTMO that allows you to load in your data in a very easy way. You just need your text file, it reads it in, you need to say what are the variables, carotenoids, chlorophyll, and so on. You need to make sure that you have both reflectance and transmittance. And then afterwards you can do the coupling with the canopy model. We allowed coupling of two models, so for homogeneous surfaces, agricultural fields, you can couple it with the SEAL model. For more structurally diverse surfaces such as forests, you can couple it with inform model. In this way, you do the upscaling of your leaf data through the structural upscaling towards top of canopy reflectance. Then afterwards, in ARTMO, you can do all kinds of other applications. So you can visualize it, you can further upscale it to radiance with our top-to-tower toolbox. You can emulate your own model, or you can use it for retrieval applications. Just a few examples of leaf data being upscaled to canopy level for different LAIs. So this is carotenoids and chlorophyll that was measured. And we have now it plotted for two LAI tags. This is with the SEAL model, but the same can be done with the inform model. So for various LAI, so our leaf model data upscaled for different LAI configurations. Once you have this kind of data, you can think of all kinds of applications. For instance, you can put it into the machine learning toolbox, develop a machine learning algorithm that then can be used for your satellite data, your drone data, whatever. So you can use leaf data, you upscale it, you can develop a retrieval model, and you can use it for your own drone data, satellite data to do mapping of your leaf variables. Here we tried it for chlorophyll, carotenoids, and then the ratio of both. It works quite successful. I had no time yet to map, but now the model is developed, so if any image you can apply it to, and you can map these variables.
Joachim, I suppose these are results on synthetic data?
No, real data, upscaled with SEAL, and then applied to the retrieval model. So real leaf data, you upscale it to the canopy model, right? And then you develop the retrieval model.
Okay, but the real data is only on the leaf level?
The real data is only on the leaf level, yeah.
But then your chlorophyll retrieval is then validated against a wet chemical chlorophyll.
It's validated. Sorry, this is we use 70% for the training part, and this is the 30% of the validation part. So you use the same data set for the training and the validation.
But it's chlorophyll measured as in milligram per square meter
Yes.
leaf area from a wet chemical
Yeah.
analysis,
Yes.
or from a synthetic.
It's measured in the laboratory. I didn't do that. I just got the data from Sharif and Wittenberger.
Because I'm really impressed. R squared of 0.99 is really killer.
Yes. I was also surprised. Also with machine learning, actually I run it against 15 different types of machine learning algorithms. So neural networks, support vector regression, Gaussian processes, and here I show the best performing one. So the other ones are a bit lower, but yes, this is what it does. I think the very good results, because of course you upscale it for, let's say, different LAIs, configurations, and since there is this part of synthetic data into it, I think that's what you refer to, right? So they are, it's perfect data, so to say. So typically you add some noise when you want to apply it to real data. That's true. Okay, so with this maybe we conclude. So to tackle objective 1.3, we plan to organize intercomparison study of the fluorescence relative transfer models at the leaf scale and the canopy scale. And to tackle objective 1, there we developed a tool into Arcmo to upscale leaf data towards canopy scale. And with this I would like to conclude, to close the presentation, and then the next presenter will be about more ray tracing leaf and canopy models. Abdel, the floor is yours.
Is there any questions?
Rochelle.
Yeah, thank you. It's very nice to see that, this application that you just give the leaf profile data to the model and then it's upscale. That really, but as Martin already raised, the R square very high. R square of 90 or something for chlorophyll is is amazing.
Yeah.
But I think it's also what we should also here note is that the leaf chlorophyll measurements, I didn't hear what source was the leaf chlorophyll measurements coming from, but actually the measurement strategy that it has been taken for the measurement in the field is very important, because we know that the way leaf chlorophyll is measured in the field is whether it's, the leaves are randomly collected within the canopy, whether the leaves are collected from the top canopy, or whether the leaves are collected from proportionally from all the layers. It actually very much will be.
That's a very good point. Indeed, with these canopy models, we assume homogeneous leaves, right? Indeed, it doesn't take into account differences between top leaves and bottom leaves. So you need to make sure that your data set is well representing all the variabilities of the leaves in the canopy. Exactly. Okay, so if there are no more questions, we can come for the next presenter.
So the next presenter is Abdelaziz. And the title of his presentation is Fluorescent Modeling from Leaf to Canopy based on Monte Carlo Directly Transfer Simulation.
leaf to canopy based on Monte Carlo ray tracing simulations. So the plan of my presentation is as follows. I will present my problematic, then radiative transfer modeling in the two scales, leaves and canopy. Then some simulation result will be presented and discussed. Finally, I will conclude and give some perspectives. So, why we need a 3D radiative transfer model? In fact, it is known that this model allows accurate simulation of physical phenomena, in particular when the medium is heterogeneous. So, here the medium can be the leaf or the wall canopy. Also, it is possible to invert this model even though they are complex, using lookup table which is pre-computed. Also 3D models can be used to validate 1D models. For instance, for ROM-C web tool, we use something like that. So let us move to present radiative transfer model. So we start with leaf, and here a brief fact about its anatomy. So it is composed of 4 layers, upper and lower epidermis, and then between them we have palisade and spongy cells. If we make a zoom and see the interior, we see the chloroplast, which are assumed ellipsoidal shaped. So the chloroplast will contain the chlorophyll and the other pigment. So for to determine the radiative regime, we use Monte Carlo ray tracing. It means that the mockup is divided into voxel, and large number of radiation will be traced like that. So we can have transmittance or reflectance if the radiation exists in the top or bottom of the mockup. Here 2 phenomena have to be taken into account. Scattering if the radiation reaches the interface between 2 mediums, or absorption if the radiation is traveling along a homogeneous medium. Then to take into account fluorescence, if the radiation intercepts the chloroplast, it will emit fluorescence, and this new radiation has to be traced as the original one, and so we obtain backward and upward fluorescence. Here I would like to note that for all this computed parameter, we estimate the directional distribution. It means that in this level we assume this, we compute this distribution, and then in canopy level we will use it. It means that in this case the leaf are not anymore assumedly Lambertian. So for leaf canopy coupling, so using ray tracing, it is almost just the same thing. The medium is divided up into voxel, and we find the first interception. Then after interception, there will be scattering, and the scattering here is according to the bidirectional distribution of scattering, reflectance, and transmittance. So the radiation will be scattered and so on. Then to compute the reflectance, we use the classical photon spreading technique. It means that we will send radiation in the direction of the sensor. If it is not intercepted again, it will participate to the reflectance. Then to take into account the fluorescence, after each interception, the leaf will emit fluorescence, and this second ray will be traced, and also to estimate the radiation received by the sensor, we use the photon spreading technique. So let us move to present the result. Here I present the upward fluorescence and reflectance for different incidence angle, and here we assume that chlorophyll equal 50 milligram per centimeter square. So here we plot different spectra, reflectance, apparent reflectance, and energy of photosystem 1 and 2. In terms of reflectance, we see that it increases with the incidence angle. Here there are two reasons. The first one is the specular effect that increased, and the second one is the increase of the optical depth. Then in terms of fluorescence, we have almost the same result, but here I would like to note that even though this leaf don't have the same cross-section, we assume that they receive the same intensity. Why? To have comparable result. Otherwise, we have to divide the value by cos theta, but I don't do it to have this result comparable. So this small, there is small decreasing of fluorescence as a function of the zenith angle, which is due to the increase of the optical depth. Then I tried to divide the chlorophyll by 2, and we see that the reflectance increase, of course, because we have less absorption. The fluorescence at the red edge decrease because we have less creation of fluorescence, but fluorescence in the red domain increase because, of course, we have less creation of fluorescence, but also we have less absorption of fluorescence. Okay, so the balance here is positive, and we have more fluorescence. Then for the same result, but for downward fluorescence and transmittance, if we compare them to the upward fluorescence and reflectance, we see that we have lower result. Also, we see that the transmittance decrease with the zenith angle due to the increase of the optical depth. The same thing for the fluorescence. Here, another result about the probability distribution of the emission of fluorescence. Here, for the upward fluorescence, and I choose the wavelength 761 nanometer corresponding to the oxygen absorption. So we see that the probability of emission decrease with the optical decrease with the depth. This decreasing is more pronounced for high zenith angle. In fact, it depends on the optical depth. The more the chloroplasts are in the depth, the more they receive less light, and the more they can produce fluorescence. For that, their possibility of emission is lower. We see also that when we decrease the fluorescence, chlorophyll to 25, we see that this distribution is less, the variation is less pronounced because the optical depth decrease. So for then for the downward fluorescence, we have almost the same results. I will not comment. Then I present here the angular distribution of fluorescence and reflectance for the leaf. For theta s equals 0, we have almost Lambertian leaves. Then when theta s increase, for reflectance, we see that there is the bright region and the forward direction, which is of course due to the specular effect. Whereas for the fluorescence, we don't have this increase, of course, because the fluorescence, it is not created by this specular effect, but we have something like the hotspot effect, as we can see here, close to the backscattering direction, the same thing here, because I think that for the fluorescence, fluorescence, it is mainly...
You are in 10 minutes.
I have to speed. I will not explain this effect. So let us move to present the... otherwise I can explain it. Let us move to present the result of canopy, fluorescence, and reflectance. Also, we continue to discuss the angular distribution, and here we compare planophile and erectophile distribution. For reflectance and fluorescence, we see that we observe the hotspot effect and the backscattering direction, and for reflectance, we see in addition the forward direction, the bright values here, which corresponds to the effect of reflection. So then I tried to plot the ratio between fluorescence and reflectance. So why we need this ratio? In fact, the ratio between fluorescence and reflectance can determine the best sensor angle to determine the maximum value of fluorescence, to be more sensitive to fluorescence. It means the highest value. And we see for the planophile case that we have maximum value close to the nadir observation. But in the erectophile case, we see that almost we have Lambert distribution. Then here we compare the spectra at canopy level, and we compare planophile and erectophile distribution. So first, in terms of reflectance, we see that the reflectance is lower in the erectophile case. This can be explained as follows. If leaves receive the same energy, in the erectophile case, it is known that, in theoretical point of view, that it is less probable to exit the medium by the diffuse radiation. For that, we see more absorption. More absorption corresponds to less reflectance. For that, also we see that we have a decrease in the fluorescence and the red band. In the erectophile case, we see that here it is less there, because the fluorescence energy can explain it as follows. The radiation in the erectophile case cannot exit the medium easily. It means that it can create more fluorescence. Then, after creation of fluorescence, the radiation, of course, cannot exit easily, but in this band, the effect of chlorophyll absorb that, the fluorescence will remain the same, and it does not go to simulate fluorescence at both leaf and canopy scales. As a result, at leaf level, we see that fluorescence is the highest in the upward direction. Fluorescence emission probability decreases with the depth. This phenomenon is more pronounced for high incidence and high chlorophyll concentration due to the increase of the optical depth. Also, we showed that fluorescence in the red edge increase with the chlorophyll concentration. Conversely, the fluorescence in the red band decrease with chlorophyll concentration. At canopy level, we see that the hotspot effect is observed in fluorescence, angular distribution. Also, we showed that fluorescence and the red edge remain almost constant as a function of the leaf average angle. which is not the case for the red band, and we see that it decreased as a function of this angular distribution. So what next? For our work package, as we would like to compare different leaf models, we have to study sensitivity inputs and outputs and propose a protocol of comparison. Validation of the fluorescence at leaf level is among our perspective. For that, I would like to visit laboratory experience in leaf biology and fluorescence to integrate other pigment in the proposed model. Also, we would like to validate the fluorescence at canopy level. It can be done in collaboration with the work package 3, for instance, by using drone with multi-angular distribution. Then the model can be used by everyone who wants to use it, and validate with actual data to tackle actual problems. And thank you for your attention.
We have time for a short question.
Thank you for this presentation. If I may ask, how did you decide the grid size for the 3D modeling? Were you based on the wavelength?
The size, the grid size?
For the simulation?
Actually, for 3D models, we would like to have something like 100 triangles per voxel.
Along a triangulation, how do you triangulate?
Calculate what?
How do you triangulate? How much is the how long is the edge of those triangles?
Actually, it depends of the form. If it is smooth form,
Yes.
I decrease the value, and for very small form like chloroplast, the triangle are actually too small.
Okay. Thank you very much.
We should continue for the next speaker, and if you have any more questions, we can ask in the coffee break.
So now it's Leah Halleck.
Yeah, just arrived.
Okay, good. I have time.
Maybe we can change to the next one so you have time to rest a little bit before yours.
So Leah cannot present. The speaker was Pastor Leah.
Oh, I found the memory stick, so I can try to be
No, yes, but the other presenter wasn't here. So it's from the Bulgarian Academy of Science.
Yeah.
Oh, yes. So,
¿Ya lo diría o...?
Yes, I have my memory stick.
Okay.
so just to be sure, so just to be sure that people is aware of the presentation, so next one will be the Bulgarian Academy of Science. And then we will have the coffee break, and then please during the coffee break, Swan, Paula, Pilar, Martina, and Sebastian, please put your presentation on the computers. Thank you.
Okay. It's the right one. describe what they are actually doing and which methods they actually coded into the platform to achieve. Okay. The platform itself should be ready in the end of this year because the Horizon 2020 project will end with this year. So the platform aims to produce three estimates of parameters, lead traits, particularly lead traits which are generated by prospect models, or the topic what this platform is aimed to generate. Satellite data is not available for particular moment, then it is estimating and reducing, giving uncertainties, and uncertainties are then higher if the value has been generated based on the prior knowledge if this particular moment was far away from some cloud-free satellite image acquisition. The central idea is to combine together range of different satellite sensors, high resolution and coarse resolution. Particularly currently coarse resolution is used for atmospheric correction for higher resolution satellite data. And then also including optical and microwave sensors. The project is coordinated by Netherlands University of Leiden, and hence also a large part of the program is coming from their side. The other three bigger partners who are actually producing main part of the code and who would be the team who is actually capable to explain to test users in great detail how they are currently coding and programming this platform is from Brockman, then LMU and University College of London from UK. The smaller partners include our team from Tartu. Our main responsibility will be ground
are then all combined together in inference aging and from biophysical parameters. So these are now like leaf chlorophyll content or leaf area index or albedo. The biophysical parameters are then used to generate post-processing. Post-processing includes diversity metrics and disturbance metrics. Here is the example output from EODAS, which was actually the precursor for the particular platform. This part of the engine was already existing when the multiply has been built on it. Now you can see the green lines indicate when has been satellite observation actually taken. And here is the biophysical parameter absorbed radiation, fraction of absorbed radiation in this case, which is produced continuously for the whole period, and when the gap between the acquisition, actual satellite acquisition is longer, then the uncertainties are increasing. And when is the next acquisition? For example, here is obvious that the priors are giving different value than what is estimated if the satellite data has been also present. Currently, it's not producing this style of visual output. The testing currently is in Jupyter Notebook environment, so that whoever would find something interesting in it would be welcome to join with the test users to. And currently, it's also possible to give feedback about what kind of visualization should be actually included into the platform for platform itself, if it's starting to download all the satellite data for given region, then it's taking quite a long time to work, so it's not possible to do some demonstrations that are really running it. But no, I didn't watch that time when I started, but if you're interested, it would be possible just to try to execute
you have one minute.
Okay, then yeah.
So what can we do exactly with this?
Now just then if it's 1 minute, then I will not try to execute in some web, but with the web browser it's possible to access with this link to the notebook to run the platform itself.
But then, can you go one slide? So in this, if any of us go to this website and use this password, it's able to run your platform?
Sorry?
I can understand. So if you give a link and a password.
Oh, okay. The password was because that's actually my own password. If you are this user, you will get your password. Just that if I would have been talking faster and having the time then in order to log in, just need the link and the password, and then you can run the platform.
Could you please show us again the site, the website of your how you're going to this?
So if I have a study, so thank you for your presentation. If I have a study site and I want to have this beautiful, seamless, gap-free estimates of chlorophyll and sun moisture for any site on the world, I mean, when is it available? And is it available at all? And is it available for me as a user?
It has been mostly focused for Europe, but some test areas are, for example, the original crop data was coming from US, so there is in my understanding there is no physical restriction, you just give the coordinates of your region of interest. And since it's just going to download it from which takes time. So, but in principle it should be possible to run it for any region.
Is it on demand? It runs on demand when I put the demand with my study area and my time request, and it's running processing, right?
Then it's going to give the region and your time period of interest. And then it should start to download the data to make the all corrections, which is a slow part, and then if somebody has already made the corrections and this data is stored, then comes the question that to run the platform in some region where the data has been already pre-processed, it would be faster
and do I need this login that you provide to do so?
Actually, if you express your interest, then you would get your own password.
So this is public domain or is it a commercial product? Is this a commercial platform or is it public domain?
This platform itself is supposed to be public. Now the question will be where it's going to be hosted. It's not currently entirely sure. It may be the paid server where it's hosted, and then you would need to pay to have access to this computing facility.
Okay. Sorry, I fear we need to continue. We will have the last presentation before the coffee break. So please ask all the questions you want. Feel free. That's why we have coffee breaks. And And we are going to continue now with Lichens. I'm going to present clock-retrieval parameters from drone, or validation from drones, as far as I understood. So thanks, Lea, thanks a lot, and let's go straight to Lichens. And meanwhile, please, during the coffee break, whoever is presenting after the coffee break, please put all your presentations already in the laptop, so we can speed up later. Okay, we are a bit tight with the time right now. We are a bit delayed, but thank you.
The actual presentation will be presented by Asian students of ours from the Remote Sensing Engineering Department, Space Research and Technology Institute of Mechanical Science. But I'll just make a short intro because I just wanted to give her the floor. Her topic now is most suited for this working group. First of all, I have been working
Can you speak a little louder, please?
a little bit louder, okay?
Thank you.
I have been working not so intensively with modeling, radiative transfer modeling, probably some years ago, when I have been doing my PhD. At that time I didn't have a supervisor who was capable to lead me towards the upscaling issue. I faced it seriously because I have been studying vegetation stress for conifers, but hopefully some years later I have the opportunity to collect the data for fetus experiment, which was part of METEOC project funded by the European Geological Society. It's a GRC project. The project was, the fetus experiment was in fact made within the GRC premises of the group of Natingobron. And all the live data that we have collected is still there via the web. You can access it for your modeling studies. Let's say it's a hemispherical reflectance that we have collected using various pieces inside and outside of the GRC's premises. But anyway, this is a short, brief intro of how I have touched and tackled the modeling issue. Unfortunately, I don't know what was the status of Rami now, because Rami was run exactly at the climate risk management unit. But I see that within this course action there is a powerful example that the intercomparison of models will continue. So the presentation is the most recent thing that we have at our department. And I'll give the floor now to the slide. Thank you.
I will just take 5 minutes of your time because our group is a new group to this construction and Bulgaria also. So why we are here and what we maybe can provide.
Can you speak a bit louder?
Louder. Okay. I wanted just to show 2 examples of study that we made with my colleagues. The first one is about crop canopy parameters retrieval, and the study was started when we tried to actually convince the Bulgarian agronomists that remote sensing is a valuable tool for their everyday work. question was still which is the best model to retrieve one parameter. And what we felt is that we had defined criteria that will tell us that we will accept the model or not as suitable. So the criteria here is that the normalized mean square error of the cross validation is below 10% or close to 10%. So the model as a whole is high accuracy. Then the normalized root mean square error of when we plotted the image, the model to the image between the estimated and measured values is less than 10%. And also because for most of the parameters, the Gaussian progressive regression was the best model, or its variance with band analysis for dimensionality reduction. We felt that we wanted to have the lowest possible uncertainty, so most of the areas should be retrieved with the highest possible uncertainty. So this is why we had the uncertainty less than 50% for at least 60% of the area. This is what were our criteria. And what we found is that among all the parameters that we studied, only two actually hit: the nitrogen concentration and the plant height that reach or are very close to this criteria. What also is feasible is that in both cases the short infrared wavelengths are amongst the important bands that were selected by the model. So having said that, we felt that so this is telling us that there is a relation between those parameters, but it doesn't tell us why those one are not the biomass and vegetation fraction. We were expected to have vegetation fraction. So why for most of them the sphere band is important. So this is why actually we try to tackle the problem on another side by the physical models, and so I'm very happy to be there to learn all about RTMs. So this was one project. The other one is completely different, and this is just to say that we all know how difficult it is to collect data, how time-consuming, and I really feel that the drone can be used for some of the cases as in-situ data, ground truthing. So maybe for our study of height of the plant, we could use the drone. Here I use the drone to actually calculate the flowering period of rapeseed, and it works quite nicely. And just to say that we had a contribution financial, and also we work very closely with agronomists from Koteva Agri-Science. And for possible scientific mission, you may know that Bulgaria is a PEC state for European Space Agency, and there is one last call which will probably be open before the end of the year. So if we hydrogen. So this could be a possible project for the scaling up. And the last thing maybe you know, I didn't know until recently, it's more like resource for temporal gap. It's that the company Planet provides for scientists remote sensing data that is with high spectral and temporal resolution. So maybe for testing it could be. This was for me. Thank you very much. So I suppose there is no time for question, or if there are questions, either way I'm available. We are available.
There's time for a quick question.
In your nitrogen retrieval tables,
Sorry?
in your table for nitrogen retrieval, you had BW, what, AW? I wasn't quite sure what that meant. Weak plus BW?
This is the data set is before winter and after winter.
Oh, sorry, right, yeah. Okay.
I try to go fast. So because we studied really only those two periods. Before winter, if the crop is developed enough to have a good
So it was
chance.
basically just merged.
Yes, just put, yes, yes.
After winter.
So we had the institute data for a week before winter, institute data for a week after winter, the same for rapeseed, and we tried different models to merge the both, to do only wheat, to do only rapeseed, to do only wheat before winter, after winter, and see how what the results are. Try to explain, but yeah.
There are no more questions. Maybe we can go to the coffee break. Keep on the schedule. Thank you.
Okay, so we have a coffee break for a half hour.
Slam the door in the front.
get 3 new publications. I think, why? She's never stopping now. How do you write this? Huh? You have so many already this year, no? No? But why do I get all these Google alerts?
I mean, as a first author, do you mean in total?
Everywhere,
Email.
they don't distinguish.
Yeah, well, okay, so in the last few years I've been working with a number of PhD students, and that's why they just, the results are coming out now. So it's
That's a good feeling, yeah.
but it will be quiet somehow later because I will after this year I have only one PhD student, well, 2 PhD students, but then I had 8. I was in a time I was involved in 8 and then gradually reduced and then now so it's good, huh? Some it's you have a time period in your life when you are very active. So
I also had a closer look to the paper using Inform for the forest of chlorophyll. We discussed a bit in Brno, no?
Yeah.
It's not bad.
That's
Did
one
you
explanation.
rescale a bit between the two, or did you use the model as it is and reflect? I mean, you did not.
What do you mean by rescaling?
Might be that there's some for example, one data set. For example, the atmospheric correction could be not
so actually, so what happened is that I had the reflectance data from the 2 data set, and what I did was generated basically created 2 lookup tables with a different value.
It was nice. The paper is nicely described, it's well illustrated. No, I could.
So finally, did you review or not?
No,
Because
that was not this one.
It was not?
No.
Because I got the message from Frick that he sent me the reviewers comments and that he said, Roshana, I have received the reviewers comments from 2 reviews. The 3rd review I don't expect to be written, but I have told them if they want they can still send us. But
no, at one point in time he asked me, maybe are you ready? I have enough.
Já jsme si tak obejdu z
But all the they just ask you if you have something to give it now, otherwise we have.
because actually I thought only one of the reviewers. Because by the comments I received,
Because really it's good, it's useful. I mean, I don't.
because at one time I received the review and then he told me and he wrote me and he said I have received now 2 reviews so you can start answering this. The 3rd reviewer I don't expect that he replied, but if he reply I will send you additionally. So I was quick and then I take this opportunity because it's 2 reviewers I immediately correct and let him return. So and then I did okay.
What would be interesting is
because
to
I
put a
just
bit
also
in
published
Android.
one also in remote sensing. I just published also one in remote sensing.
I mean, what we should better tackle in general is I mean, now you have some prior information from the field work, but we have very little information about the intercorrelation of the varieties in reality. So you draw randomly from the distribution, but still it's independent from parameter to parameter, except perhaps that you distinguish. Did you distinguish between conifers and?
No, it was only in the conifers.
It was only conifers. Because this is what I do, I have different parameter sets for the two.
Yeah.
So, because they are different.
The thing is that I use the data from one of my PhD students, and therefore I was a bit, I didn't want, we collected a lot of information, but I didn't want to, ask him too much. I said, okay, just give me the choroid data, and then Yeah, you know, so it's also data sharing between the faculty, like it's a bit, they say, oh, you know, there's a kind of sensitivity that they need to collect by the PhD student, you know, it's more than PhD students, so it's okay. So I said, okay, it's my PhD student, he was the co-author on that paper because he was the co-author, and then there was another student involved with that because he helped on the chemical measurement in the lab. So the two students who helped me on the lab, I put them as co-authors. But because there were a lot of sensitivity, I didn't look at those papers, the relationship between the parameters and how they, because then I had to ask him basically everything, all these data.
And then I noticed in all your papers you always plot this, you know what we did also in our paper, the absolute error then between the difference. And it's always in the infrared band which pops up as badly modeled. Do you have any idea why it's this band?
¿La Petra vive con Bruna o la zona con la avenida atrás? La figura de la gente.
No, Bruna lo ha pasado para pasar.
It was in the basically the bands in the infrared region where they want. You know why? Because basically, well, in the paper I used for chlorophyll in using E4, the bands from the near infrared has the worst basically error. Well, you can have there can be a lot of factors actually. One of the things is that for the leaf chlorophyll, I mean in the case of the leaf chlorophyll, where the scattering basically causes in the near infrared region, and can be one thing because it's how do you want to mean the absorption of the chlorophyll is happening in the basically red edge and it's mainly affecting the red edge and the red band. So the near infrared band, okay, the scattering.
So always but this is the band which is, let's say, affected by the lowest number. It's only affected by the area index, the angle, and then...
No. Because if you...
no effect
well,
of
there is the effect of leaf dry matter. We have shown that. Dry matter. So there is an effect of nitrogen. So it's okay. So nitrogen, leaf dry matter, I mean in the recent
But the
study...
dry matter is all the other bands also.
Yeah, but particularly in those areas. I mean, look at the recent publication that we have shown that the leaf dry matter content and nitrogen, particularly in that region, are basically, I mean, those regions are really sensitive to leaf dry matter content and nitrogen.
Yeah, which makes sense. But still, I would expect that, let's say, the near-infrared is the best model channel, and it's always the worst. Always.
Yeah.
I've never seen a single paper where it was not the worst.
You know why? Because first of all, in the case of the leaf chlorophyll, I can say that okay, the data I have, the field data is leaf level data. The data I have as a canopy data, I mean the satellite is the canopy data. So that canopy spectra is affected by LI and many other factors in the near infrared.
Yeah, but the same factors affect also the visible in the sphere.
Yes.
So in the near-infrared...
In our own studies that mainly short wave infrared and near
any plans to integrate fluorescence into Inform? I mean, this could be something we could do together, because this is what Jochen was also suggesting, you know. I mean, it would be a pity. More and more people reuse now Inform, and I'm very glad. But we should...
It's me who pushed these people to use Inform, don't forget. Because I push all my students, you have to use, and I convince Andrew that we have to use Inform.
No, but it could be that other models are better. No, this I would never do. No, then I would...
We tried it and it was good, so it's okay.
Yeah, but you should try perhaps the second model in parallel. Could be... But what I want to say is, I mean, we would be wise to include some fluorescence stuff into Inform.
I'm okay.
So, but do you have someone who's... I mean, it cannot be that complicated. I mean... it's just as they say it. I mean, it's just a different source of energy. So, and we would be open also to these new upcoming satellites. I mean, they all focus on...
Prisma is now launched.
Yeah, I've seen it. A couple of days ago, you know?
Last week.
Last week. So, I don't know, do you have someone or not?
I don't have someone now, that because all are already on their topic. All the PhD students are now on their topic. Already the
Settled. They have enough to do, yeah?
They have enough to do. If you ask them extra, they will. But
you mean we need to do it ourselves?
We need to do it ourselves. We can do it ourselves.
No, it cannot be that complicated.
No, I think we can do it actually ourselves.
I mean, we could also look,
because
usually...
once successful, then the students would...
Did you ever test to replace, let's say, Prospect by some other leaf model in Inform? Did you ever test it?
No.
Me neither. Could be that perhaps, you know, especially for conifers, who tells us that Prospect is the best? I don't know.
Yeah, I tell you, because I don't tell, okay, like 3 years ago, we did a study on the conifers, only at the leaf level. And then we showed that Prospect could actually do well using Prospect.
But it's not sure that another model is not better.
No, but I would be interested to do that if you I think that would be something new research. I want to get something new. So I'm now exploring I want to do something.
But you have seen also what I have done on this object-based inversion, no?
I have seen your papers.
Yeah. So the same is missing for Inform, but the principle is the same.
The paper we published in 2012 is not that.
No. No, it's object. Let's say you take the reflectance from an object, but you don't look at the intercorrelation between the spectral bands. No, we haven't done this for now. It has never been done. But there's for sure some information because, let's say, you know, texture is nothing else as what I use. It's just a physical description of texture, what you see.
This means that the data you use should have a very good, you should have really very good reflectance data. I mean, if you want to take texture. And something like with like the paper you published on that object base is used hyperspectral data.
Yeah, but it applies to all kind of sensors. The idea is...
I don't know, because I'm not sure if...
Look, for example, in Inform, one parameter is, for example, let me take one, stem density. Okay? So in a managed forest, the stem density is not that different here from the next place. It's more or less the same. You know? So you should not estimate the stem density for each pixel individually, but for the whole forest simultaneously. That is the idea. Like for Ala and the crops, you know? So stem density is a good candidate where we would certainly gain some additional accuracy if we would not do it pixel by pixel the inversion, but let's say in a moving window, or if you have boundary defined by polygons, can be also done in this way. Either a moving window or a defined boundary.
But defined boundary, what do you mean? I mean,
A stand.
we need to have
stand.
a forest
I
land
mean-
cover. We need a land cover.
Yeah, I mean in the Bavaria case, it's a natural so it's not really managed forest. But let's say in a typical managed forest, you see the boundaries. They have here spruce, there you have another. I mean in agriculture it's easier because you have really fields, but in forestry, in managed forests, you have the same. You have stands, what they call stands. Not in Bavaria because it's a natural forest. So it's
But from
more
the Bavaria, we have the.
How are you doing? Hello. Good? Oh, always
You do
3 times.
3 times.
Yeah, I know. You're always getting me on this. It's difficult to
Very difficult to hear.
I can announce it now during Portuguese.
Please speak because I cannot. I forgot my glasses, so I'm using my sunglasses to see the. But I also
Seeing is okay. Small. Seeing is okay.
also not good.
That's a bit. It's relatively small for the title.
Like this.
But we have to play with things that we have. They're already well organized here in general in this university. I think the hostages are very smooth, but I agree it's a bit small for our ITC standards. I had the feeling she saw the slides for the first time.
Yeah, sure.
I could not even.
What happened, Clement? Austria. They didn't manage not to be in the registration. How did it happen? Because you were registering late, I think. That's why, right? But I'm glad you're here. You made it.
Yeah.
Huh?
Always.
Always. Now it's the second time we're meeting now. Can you imagine? We have a fantastic networking now. Well known? Well known? 6 weeks later?
We are just
discussing the new steps.
Oh, yeah. Very good.
You're interested?
Inform. Oh, yeah, of course. Yeah. Inform 2.0 or 4.0.
We are thinking of how to integrate the fluorescence in the.
Yeah, come on. That would be good to do something about
No, really. I would be.
What do we need? We need PhD students, postdocs, or we do it all the work ourselves?
In principle all, yeah, but we have nothing. So we have to do it ourselves.
Do it ourselves, okay. I mean,
I can also put it sometime.
just we need a mastermind in the back. And I can also already imagine who that could be. Huh?
Yeah.
A mastermind who has, who's coordinating a little bit.
Yeah. It's okay. I mean,
I can do that.
I can spend some time. I'm willing to spend some time myself.
Yeah, me too.
I take this charge on me.
We only need a plan. We have to.
Yeah, we need a plan.
We need a deadline. Something where we say like, okay, we have a deadline when we want to reach that and that milestone. Otherwise, it's going to fade out into 3, 4, 5 years and nothing happens. But if we have at least an objective, say like by that.
3, 4, 5. I expect this to be done by end of this year.
Yeah, exactly. That's what I mean.
Is it far? No, it's already long to go. I mean.
Yeah, no. I'm just saying if we don't set anything, it might fade out. Right?
In this inform version that everyone is using, how do we handle the bark reflectance? Because we had sometimes included, sometimes removed. Which version are they using? Bark reflectance.
I think
in this Atmo website.
I am not sure.
Bark is not
let
in.
me tell you,
Bark is
I'm
not
not sure. I have to double check this. But in the last 2 years, 1.5 years, I had a postdoc, which she had no knowledge of remote sensing. She was a plant physiologist. She came to me to do a postdoc with us, and she wanted to learn remote sensing. So actually, I learned her everything, like what is remote sensing, how to use a spectral, and then I designed a plan for her. How to do sampling, what to sample, I supervised her throughout. So now I have a rich data set, and I have put this condition that this is my plan, is my proposal, is my idea. I'm teaching you everything. So the data is shared with me, and then I will tell you what is this, but I'm planning to write one article, and she will write one article. But then, like one article, it's my idea, it's my paper. in that data set, if I'm not, I have to double check it, but if I'm not wrong, in that data set we also have measured chlorophyll fluorescence. So if in case that thing, that incorporation would come into, I mean, for the info, probably we can use that data set. But I have to double check the data. I'm not sure if we measured also chlorophyll or we also measured chlorophyll, because we did the lab chemistry, and then I think we also collected, we also recorded fluorescence, but I have to double check it.
What I got to do now is I have to get the thingy going again, otherwise you're going to be late totally.
Go ahead. Yeah. So she collected, you know, once I was discussing with Andrew about a possible postdoc application, and then Andrew said, "What do you think? What should she work on? And then in this, I said, okay, I have something in mind that I want to test for years, but I have never had the time and basically time to do it. So it's we'll contact them. I'll get it.
After the next break.
Sometimes not always perfectly here in the last. So I'd like to ask the next speakers to try to speak not too fast, not too slow, and to speak loud. Yeah. And please, the jurors, if you see they don't stick to that, don't be shy to say, hey, I speak up a little.
Okay. Let's go back, everybody, to the seats, because Sean is going to start the presentation. And before he starts, I'd like to ask who did already the questionnaire. Who is to be? Sorry? You started and then it reset itself. Okay, you are close to be reimbursed. The rest of you maybe not. So please remember about the questionnaire, and if you didn't do it, please try to do it during these days. Okay? Thanks.
Okay. It ran away. Oh, there it is. Okay, so changing gears a little bit. So I just had to add in my student's name really quick. Okay, here, Lisa. So I do a lot of applied research, and we're looking for picking up and adding some of these models to the data we've been collecting over the years. So it's sort of a general talk. And it's a lot about different uses and ideas for using this moving forward to solve some real-world problems, you know? So satellites, UAVs, and mobile phones for agroforestry. This was my PhD, just so you know a tiny bit about me. So it was hyperspectral remote sensing, combining topography, satellite data, airborne hyperspectral data, and field measurements. So combining sort of topography, hydrology, geographical variables with some spatial modeling, statistical techniques for species classification, and we focused on one species and the health of that species across geographical variability, and looked at how its health responded to its position in the environment and different combinations of water stress and air pollution. And so we started doing some spectral modeling on the side of the physiological assessments and the different statistical techniques to separate out individual species to look at their ecology. And now moving forward, so I'm now sort of presented with a different challenge at the University of Barcelona. So multi-scale agroforestry, plant ecophysiology, and then high throughput phenotyping and precision agriculture. So we sort of bringing it down from airborne hyperspectral. Now we're UAV multispectral, and we're looking at trying to find solutions to what is often defined as a scary picture here. So different factors affecting productivity of not just crops, but also forests, forest species, productivity, and then different ways that we can counteract these factors through plant breeding and improved agroforestry sort of management. So going from the scary picture to feed the future, a lot of what I do, there's some agronomy and management, but crop breeding. So we have, for example, one study, it's 24 varieties of wheat grown in 3 replicates in southern Spain, central Spain, and northern Spain with nitrogen, drought, and heat stress tolerance. So I think it could be an interesting data set we've been collecting over the next couple of years for some of you modelers out there. So this is some of the scary picture. I've been talking with a lot of people and doing some outreach, and you show this to a general group of people in the public, and they get a little spooked about things changing and the heat coming up. And so I think we're going to see plants responding differently going forward, and that's why a lot of these scientific missions have been moving in that direction. Well, we know it's getting hotter. Don't need to explain it too much to this audience, but I had a project recently where they tried to combine climate change with philosophers and scientists and artists, and it was really called After the End of the World. And so they're looking at trying to reinvent ways moving forward, and I think some people are spooked about it, and being able to present them with some solutions to monitoring and improving understanding of a changing planet will help calm a lot of this public anxiety, and then you can have fun with it. And once you hang out with a philosopher who declares that radio transfer models will be after the end of the world, then you know it's time for a beer, right? So anyways, I put this up here as the objectives to sort of bring it back, but of course we just saw this a few minutes ago. So scaling leaf to canopy, we are using mobile phones to collect data to try to train satellite analyses at continental scales and local scales. We're using drones, and we're trying to use those to validate the data in between, because there's a big jump going from a mobile phone or a field measurement to a satellite measurement. And so with the project, and I think radiative transfer models are a good way to make the scaling real and not just sort of like a correlation between different levels of measurements, but something that's really quantitative. So we started with some ideas with this, the After the End of the World project to monitor changing LAI values in parks and stuff like that in Barcelona, and then using satellite analysis to look into it. We pushed a little bit further, going from mobile phones to Google Fusion apps. We started creating some open data kit projects that would feed this data into a Fusion table that you can import directly into Google Earth Engine and do massive satellite analyses. I don't know if anybody here has been playing around with Google Earth Engine. It's lots of fun. You can do a Sentinel-2 analysis for the whole continent of Africa. And so this sort of led eventually to this fall armyworm monitoring and early warning system with the FAO project that we have going now, where we took an ODK idea and they actually redesigned it all so it's a much more functional app. And you see so far there have been somewhere around 35,000 plants checked, around 9,000. Fall armyworm is a new plague that moth, Spodoptera, that's been invading Africa. And it pretty much spread all across Africa in no time. They had the army in Ethiopia smashing it with sticks at one point in time, so it was making a lot of news. They wanted to see if there was a way that we can look at using satellite data, dynamics, and ecology to get an idea about what's going on with it. Basically, my idea was that it's causing a sharp reduction in leaf area index when it hits, so we started looking at not just time series NDVI values, as you can see here, but also the first derivative. So we looked at change across time, and whenever we see a drop in change, for example, this was a documented event of fall armyworm infestation here. One of the things we ran into is we had some planet data at 3 meters and some Sentinel-2 data at 10 meters, and somehow the NDVI values were all very different. So there's a big problem in cross-validation here. You can see the Sentinel-2, we have NDVI values of 0.5 in the same field. And somehow with the planet.com data, the same calculations gives us NDVI of 0.2, 0.3. But then when you do the first derivative, it starts normalizing itself and looking at change differences. Again, even looking at between 10 meters and 3 meters, you see a huge difference in spatial scale and being able to detect different problems. So it's not just problems going from MODIS at 1 kilometer to leaf level measurements, but everything in between, we can step it up and down and figure out how to really connect it forward. I think we can start putting together things from these advanced models to real world solutions. So looking more about scaling observations for agroforestry, so we started flying UAVs to see how well some of the satellite data analyses can be applied when we start looking at sort of centimeter scale images. And so looking for basically here better data and faster results for phenotyping and some local solutions to global problems. So is it going to be hotter and drier in your region, or is it going to be hotter and wetter? You know, what sort of dynamics are you looking at going forward? So we started considering different things that would be sort of generally affecting yield and productivity. Now this may be going back this year, because I'm quoting something from '77, but we have radiation uptake, photosynthetic efficiency, water use efficiency, and these are actually all parameters closely tied to something that we can retrieve through these RTMs. And then also remembering that the long-term versus short-term water stress, we can see reductions in biomass. So that fractional vegetation cover versus the effective photosynthesis is something we need to keep our mind when we think about different types of data sets and where can we get the best accuracy from which data set moving forward if we're going to be combining these and fusing them. So we started moving on with geographically distributed high-throughput plant phenotyping studies. So using geographic location as a treatment, growing wheat in different parts of Spain, as I mentioned. We have barley in different parts of Spain as well, some of our different projects. And then trying to relieve bottlenecks to collect a lot of data, store it correctly, and pre-process it to a level that we can do some quick analysis and get some ideas about what's going on with these wheat varieties. And if we can select a wheat variety, that'd be better for the future. So we have multispectral, thermal, and then very high resolution RGB data. Just plain color images with very high spatial resolution. We have developed a multispectral camera. We're trying to measure sun-induced chlorophyll fluorescence. I think some people in Optimize, the previous cost action, told me that we could try it, but not to get our hopes up because it's very difficult. But if it would be possible, I assume it would be possible here as part of SENSECO, because we have the expertise from the whole world gathered here on a couple of these different ideas that we're experimenting with and see if it's possible, right? So moving forward with processing data from drones, you can get some really interesting data from drones, centimeter scale. Like I said, again, going from the leaf level to the MODIS to the planetary scale is such a big jump that you can make some assumptions that later on fall apart at the centimeter scale with drones. So we tried running some of the old evapotranspiration models, metric and Seaball, that were sort of developed for Landsat, and they just really didn't hold up very well because they were developed for a different scale. So I think we need to work more on fusing these scales together, and I think bringing together these different models like ARTMO would be a great way forward to test and see what different structures of thinking about these processes are really scalable and can be moved backwards and forwards. So real quick about RGB, in one of this optimized meetings I was talking to some people, they said, well, this is excellent color calibration, it's photosynthetically active radiation, and we have very high resolution. We developed some field imaging techniques through an open plugin called the Maze Scanner for CIMMYT. They're using this for breeding some virus diseases, combining different color spaces, fractional vegetation cover estimates at high resolution, and some other canopy macros trying to get at sort of broad band but high spatial resolution. So if we have one thing, can we make deal with the other one? We have some studies looking at comparisons with ground and UAV data for low nitrogen phenotyping in Africa, with some promising results saying, well, we can get actually quite a bit more than a lot of multispectral vegetation indices. And then also from RGB, we can do some excellent 3D modeling. So we built a PC with over 100 gigabytes of RAM, so we can create million point clouds and create some fairly accurate 3D models of these things. So if you're looking for 3D models of different crop types, I've got millions of data points and point cloud files, and I'm looking for new ways to analyze them. We can do similar stuff with multispectral data. We have an 11 and a 6 sensor platforms going on right now. They both use incident light sensors. So we have sensor reflectance measured in real time. We have changing cloud conditions. We can see the effect of a cloud coming over and changing fluorescence or PRI values as the day goes on. We've been mostly doing different indexes, but because we have centimeter scale, we can apply masks in the same processing pipeline. We collect a lot of thermal imaging as well, since it's hot and sunny in Spain, kind of like Aveiro this week. That would be cool still here in March, but it's quite sunny and hot. And again, even with only 640 by 512 pixels, we fly at 10 meters, we can create mosaics, and we can get pretty high spatial resolution. And we started combining it together. There's a study looking at the effects of conservation agriculture, combining high resolution RGB, stable isotopes, chlorophyll extractions, fractional vegetation cover, and then canopy temperature and soil temperature, and some multivariate models looking at different management practices on maize yield. We discovered that we had a bottleneck. The first year we spent 3 months collecting data and 9 months just extracting it. Which didn't work out very well because we were in the field the next 3 months. So we developed a maize mosaic tool, so it'll take in phenotyping multispectral data. We put our algorithms for calculating different vegetation indices into it, and it'll segment it out and give you results. So we can do about 1,000 small plots in an hour, or 1,000 trees in an hour, depending on which segmentation algorithm and which application sensor algorithm that you want to combine with. And we were working on data fusion at different resolutions. This was a study where I thought it'd be really great to combine RGB, multispectral, thermal data in the morning and the afternoon of the same nitrogen study for barley in Pamplona. But a lot of the algorithms for finding through an iterative situation in metric, for example, just didn't hold up very well. Started giving really weird results when trying to scale these down to the centimeter scale. So I think it'd be something interesting to look at moving forward. We did do some correlation networks, so we can see how a lot of these things are related to each other. They all contributed significantly to multivariate models predicting yield and the effects of the lack of nitrogen on yield. But you can see some were really off by themselves. Temperature, for example, we see a lot of biomass and chlorophyll, of course, integrated. We did the same thing. We have some common garden plots or provenance trials for trees in Spain. A lot of them have been running for 15 years now, so the mature trees. We developed 3D models of those, segmented them out, and started combining multispectral and thermal for different flights during different times of the year of these. Conclusions. I think we can see about how we can play off of we have different levels of resolution and precision, so we can get really precise measurements at the leaf level. The further we get away, sometimes we start losing precision. Maybe we can add in something with very high spatial resolution like an RGB sensor, and that'll give us more information than a multispectral sensor from a drone because we have 10 times the spatial resolution. We looked at a lot of massive data collection and crowdsourcing data collection. The example that was led by the FAO and the famous working group worked out great because people have a big problem. They want to contribute to solutions, and so we started getting lots of massive data for that. And then I think SENSECO interests. So we're really interested in if we can use very hyper spatial resolution data as an input to some of these models. If you need fractional vegetation cover, I can get that much better from a RGB camera with 40 megapixels from my drone than I can from a 1 megapixel multispectral camera, for example. We've been flying these data sets for the last 4 years, so we're accumulating different levels of stress, different years, different environmental conditions. And I think it might be an interesting data set to share and test with some of you who have interest in playing with some real world data in your model. And that's all.
Is there any question?
Just a very quick comment. I think your activities would also very well fit into the working group 3 templates. Maybe you have already seen.
Oh yeah, I signed up for 3 as well.
Ah, excellent. Okay.
Yeah, actually I liked all the working groups. For some reason I just signed up for 1 and 3. I feel like they're the best fit, you know. 2 and 4 are also good. Nothing against working groups 2 and 4.
But which data exactly are you collecting with the mobile phones and how?
So we developed an app for a mobile phone that has an integrated FLIR camera.
Oh, alright, so,
we're
it's not an ordinary phone with the FLIR camera.
So we had one with a FLIR camera. We had another one that we had a fisheye lens adapter to the mobile phone, so they could do measurements of LAI. So they just collect the data and they upload it, and then we can scrap it off the internet, process it, and then upload the database. And that was like a 30 euro adapter to a regular camera. And then for some other applications, just with a plain RGB image from a mobile phone and a GPS location within a couple of meters, which is pretty easy, we were getting estimates of fractional vegetation cover. We developed a mobile phone app also for yield estimation for wheat. So an algorithm that'll work in 10 megapixel images, just taken above wheat, and it'll count the wheat years. Again, that was a combined mobile phone for data collection, cloud-based processing.
And how many data points do you need for the yield estimations?
Well, each image will produce the number of wheat ears per square meter for that plot. And so it provides an estimation based on the square meter for the number of wheat ears. And then depending on the variety and the condition, they give some trial information, and we try to extrapolate it to yield.
Yeah, thank you.
Here you showed some interesting results on UAV data. I mean, we have recently experienced actually a lot of difficulty capturing a good UAV data. So I just want to know how was it really smooth to collect data free of noise and useful data? Because you showed very nice application of the UAV, but UAV data, of course, I'm not saying that it's not. It's very good data, and you can capture good data, but usually with a lot of noise and the radiometric collection has problems, and maybe you have to do this fly maybe I don't know 5-6 times, then you can get one data set which is actually useful. So I just want to know, how did you experience with the data collection?
We did some experimentation. One thing, for example, that was really popular for UAV data collection was these modified RGB cameras. Sort of swap out the filters and hack the firmware a little bit, and then suddenly, voila, you have NDVI at 10 megapixels. We did a bunch of testing of those and compared it to tetragram, so a scientific 1 filter, 1 bandwidth, 1 spectral band sort of measurement. And it was all over the place. We couldn't figure out, I tried correcting it 10 different ways, and we couldn't get any way to correct those. So it gives you perhaps interesting relative high resolution, relative values that were quite difficult to really piece together. All of the multispectral cameras that we are using have micro filter arrays pointing upwards for each specific to every band pointing downwards. So we're at UAV multispectral reflectance calibrated in real time. And then that also, we have fairly small study sites, so maybe I fly everything within 10 minutes. The light conditions are very similar, it's calibrated in real time. And then we can produce a mosaic using something like AgiSoft that also helps the alignment of the different pixels from each of the different bands. And the results so far were really good. So we had some plot comparisons with like an ASD field spec with R squareds of greater than 0.9 from a canopy level from a $60,000 spectrometer compared to data from a drone. And so the mosaicing can also be difficult if you don't have real-time calibration to reflectance. You need to make sure that your conditions aren't changing while you're flying. You need to make sure that you have lots of overlap between images. And even I've seen that can cause some other problems depending on the mosaicing techniques that you're using. So yeah, hit or miss. We had some studies where you're just not flying high enough or too close to trees, for example, and then you have too much parallax, too much 3D issues going on, and it can be difficult.
Oh, I'm sorry.
What sort of
Sorry,
altitude?
you added that.
Okay.
You can answer that. Thank you. Thank you. Thank you for your presentation. So our next speaker is Paula Matos from the University of Lisbon, and she will present the work that she recently did at the Antarctica.
So I'm Paula, so I'm a bit of an alien here. I'm an ecologist. I don't work with models. I'm interested in traits because I use traits as a basis to build ecological indicators of several environmental problems. This one is dedicated to climate change. So just to contextualize my PhD, in my PhD I use lichens as indicators of climate change, and I developed a tool to use them throughout the globe as an early warning indicator of the effects of climate change. But I did that in forests. So last year I realized that I went to the, so just to contextualize, why do we build these indicators? We all know about the problems of climate change and others, and throughout these years, the three many conventions, but the most pressing of them were the three UN sister conventions. So for biodiversity, climate change, and desertification, they have been asking for indicators that can be applied at the global scale. Because we tend to build a bunch of indicators, but then they are only applied locally, so they wanted something, they asked scientists to develop a tool or some indicator that could be applied worldwide. And why do you need them at the global scale? Because we have problems that are global, like climate change. So we have global observations. We need them to reflect long-term changes and to be observable at different scales. And we need indicators also that can measure the effects at the ecosystem level. So we know it is important, for instance, to track climate change, to measure climate changes in climate throughout the globe over time and space, but it is also important to have some indicators at the ecosystem level that could tell us about the impacts. So having this in mind, during my PhD I developed an indicator based on lichens, and I presented it to the UN. But those indicators, they were built basically based on lichens that grow on trees, so epiphytes. So they were made for forested ecosystems, and that does not cover the whole world. So then we came up with the idea, okay, maybe we also have lichens in other parts, so maybe we can do it in different things. And why do we measure the effects at the ecosystem level? Because, for instance, a very easy way to understand this is if you imagine the 2 degrees that are predicted of increasing temperature, they won't have the same effect on ecosystems if you are talking about a desert or an alpine ecosystem, for instance. So more than measuring just the drivers, we need to measure the effect. And why lichens? Well, lichens give us a clear response to climate. They follow precipitation, temperature, and in cases where we have other factors, atmospheric pollution patterns. you can think of them more or less as a sponge. I don't know if you know what lichens are. They are those small things that grow on trees or on rocks next to the mosses. So the ones that have color, they are not green. And they are very good as ecological indicators. So this is a lichen here, and when it's like this closed, it's dry. And just because the atmosphere gets wet, he immediately absorbs all the water in the atmosphere and rehydrates. And lichens are very good because together with mosses, for instance in Antarctica, they dominate. So they are the top vegetation. Lichens exist in almost all terrestrial ecosystems, from the north to the poles. We already use them in forested ecosystems, so now the idea is to try to see if we can do the same thing in Antarctica. Of course, Antarctica has a lot of more problems associated with it. There they dominate, so there you don't have trees. So you have now to rethink everything you are seeing about the models and everything, and just see it as the scale of lichens. Instead of trees, there you have lichens and mosses, and that's all. And okay, if we know they are very good, they track the changes. They are within the oldest ecological indicators known. So man has been using them for centuries, and since the Industrial Revolution, for scientific purposes, they have been used as ecological indicators. And they are also used for regulatory purposes. For instance, the critical levels in Europe set for the nitrogen deposition, for instance, was made using lichens. Okay, they are regarded as one of the most, if not the most sensitive component of the ecosystem. So we are going to use lichens in Antarctica, and what is the connection with this cost? I use trait-based metrics. Okay, so you all know what traits are. They are metrics that are very good to be applied at a global scale because they are not focused on species identity, meaning that I don't need, if you change continent and you change species, you can still use them. And you are used to talk about, for instance, ecophysiological traits like fluorescence or others. We also use other not so obvious for you traits, but they are easy to use in regions like Antarctica, for instance, where we don't know all the species, like the growth form. Different growth forms of lichens respond differently in this to climate, for instance. If you go to a desert, you'll tend to have more of these lichens. Okay, if you think about a wet climate, a temperate raining forest, you will see more of these or of these, okay? So their architecture is made to respond to climate around, okay? And this is just an example of a trait that we use. So where was this project done? This is in Antarctica, in the Antarctic Peninsula, in Livingston Island. So I was stationed in a small part of Livingston Island, which is this, the Herd Peninsula. I went with the Portuguese polar probe, so it's very hard. And this is to show you why the project objectives are. So we wanted to develop an ecological indicator to try and anticipate the effects of climate change for polar regions. The first objective, and it's based on lichens, which is the main vegetation there. So just for you to know, there are 400 species of lichens in Antarctica, only 100 for mosses. So we wanted to model lichen trait diversity along spatial gradients to identify the patterns of change when the climate changes. And then we want to calibrate those patterns with high-resolution imagery and to identify them to other regions, okay, to do the upscaling. So basically we do this on the field. The methodology was basically because I told you it's very hard to move there and we are only allowed to go by certain paths. So the island I was in was very steep, so you have a quite steep climatic gradient following altitude. So basically we would walk and every 50 meters we would apply our methodology. And this picture is to calculate. So So our idea will be the same. We take the pictures for photogrammetry and then we build a 3D structure of the vegetation. And then the third point, which is probably the one you recognize better here, was to take a multispectral photography of each of these squares. I didn't put an actual picture of those that I took because I arrived 2 weeks ago and I still haven't had time to treat the data. But the idea is to calculate the NDVI because we also want to have a measure of how the production of the ecosystem is along this climate gradient. So basically, I have no data. This was just to explain what's the conceptual idea of the project. So basically what we do is we go along the altitudinal gradient and we take the pictures. These are actual pictures. So the vegetation changes a lot and this can change in, I don't know, maybe 500 meters. So you have a complete shift. If you are down, the weather is quite different. So you receive rain and less snow and the temperature is a little bit warmer. As you go up, and 500, I don't know, 100 meters up, and rain is almost in existence, and the precipitation is all in the form of snow, and the temperature is much lower. And then, of course, you have the glaciers, which superimpose an extra on all of this. So the rain comes, the wind comes from the glacier, so the temperatures drop a lot when you have wind. So basically this is what we have, and what I thought it would be interesting if someone would like to apply for a short-term scientific mission with us is we have images at these 3 scales, okay? The first at leaf level, okay, this is the area you are used to, for instance. So we have the pictures. We have NDVI, multispectral for NDVI. We have RGB, and probably we have more. I have to check. At leaf, canopy, so drone, okay, flying over and then satellite. The satellite images there, they are very, very bad because the cloud cover is almost always existent. So there are very few days without cloud cover, so you can take nice, if you are lucky enough for the satellite to pass there. But we have these 3 levels, so the idea is for us to learn with someone that wants to go and do a short-term scientific mission. So how should we do this? With the extras that you are in Antarctica, this is not plants, it's lichens, but they are photosynthetic organisms, okay? And how to do this. That's it. Thank you. Do you have any questions for Paula?
Yeah, how variable was the water status of the lichens when you're doing your grading? Because as you know, it's very transient, they depend on liquid water being present.
No.
So
they do not depend on liquid water. So there's different lichens. Different lichens are a symbiosis. They have a photobiont partner and a microbiont, so a fungus, okay? The photobiont could be either a green algae or a cyanobacteria. If we are talking about cyanolichens, meaning they have a cyanobacteria, they do need liquid water. Still, they exist there. Not so much as like in a temperate rainforest, but they exist. But then the green lichens, no. Only if the atmosphere is above 70% relative humidity, they are okay. They are able to absorb the humidity. So you don't need liquid water. They still live only with snow.
yeah, I mean, they can, but well, my understanding is that's a relatively small component of their hydration can come from this absorption of moisture from the atmosphere.
No.
I mean, the crustose lichens, you look at the crustose lichens and they spend most of their time dry in these environments.
Of course, they stay most of the time, but still they can be fully hydrated just on vapor, water vapor. The thing about the time being dry is about how they withstand the dryness conditions, because Antarctica is we never think about it as that, but it's it's the driest place, one of the driest places on Earth, because
And also very windy.
yeah, also very windy, which dries it even more. But still they are, well, lichens there, they grow very small. So they can grow the measure in a few species, and it grows like 1 millimeter every 10 years. Each 10 years, okay? So you can imagine that lichens big, like one thing like this could have like 300 years. But still they are able to live. The question is how to retrieve this information. And they appear as green in the pictures, but some of them at least. But how to do that thing, how to use the data, but still you can do it. They are able, they live there, and they dominate, there's nothing else.
I mean, this growth rate is another issue, but they do grow, like I said, very slowly, so I don't know if we can't capture change over time.
Oh, you can. You can.
Because if they're growing at a millimeter every decade,
But
we
a
need to
single...
measure at that resolution to capture the change.
No, you have to think it the other way around. The puzzling thing about lichens is they are very sensitive, so they do grow very slowly. But if you change the conditions and it falls off their limit of survival, they will immediately die, and we'll see the change. I saw changes here over time in 3 years. And when I say changes, I say a complete shift. So the south of Portugal is becoming more tropical. And you see no changes in climate. Climate, when I say climate, the normal climatic measures you see, so average temperature. But the number of days with relative humidity is increasing. It's hot. So you see a complete shift. And it's in 3 years. So you are not able to see maybe a change in, I don't know, yield or production, but you will see a change in a shift if something changes. So imagine that you saw the green one on the basis, so it's dominated by mosses. If the conditions there start being wet as you move up, okay, you will see a shift in 1 year. Because next year, the species that are there, they are not going to be able to compete with the mosses, for instance. And this is what it's calling the Antarctica greening. So you can see the shifts, and it's very, very fast. But it's not measured in terms of growth.
Yeah, I guess if everyone would like to know about the short-term scientific mission, that would be in Antarctica?
Well, no, because probably I can't get anyone. So I'm applying again, so I will go, I will go again next year. But I would hope for the scientific short mission to be before that, so we can plan in advance, and next year we know what to measure and how to measure, because next year I will have drone, so I need to know what I should measure and what would be useful to take from there. But maybe we can think also about going to Antarctica. I have to think about that. Can't take over for it? It's very expensive.
Thank you, Paula, for your presentation.
I want to know something. How did you choose different, varieties or whatever of lions? How many different lions you are looking on?
I look to all the lichens that appear. So I work with the community. My lichens are in a Spanish boat, and they are coming, and they only arrive on July. So I would only know back then, because this was made only with photograph, because I cannot pick them. So, but I took samples, and I can estimate that I saw at least 50 different species that I can recognize. But again, I don't know the flora there, so I have to identify everything when they arrive.
So there are not so many studies before?
There are, but we couldn't, this is not like a botanical work, so you cannot pick and decide there, oh, it's 20 species because we don't have time, and you freeze if you are there just trying to identify. So you have to collect everything and then do that afterwards.
And how to determine the checkpoint where you look and...
How, sorry?
The points where you look, altitude and...
So the altitude varies between 0 and
300 more or less.
So did you define where you want to look?
No, there you cannot define anything. So you basically walk where you are able to walk because it's very steep and it's dangerous. So it's you go and you just do it. It's like a free. You cannot prepare as you prepare in the other places.
Okay, I'm sorry, we need to keep on, so if you have further questions, we have time to talk directly to Paula. And we are going to keep on with the next presenter, which is Pilar Martin from the Spanish National Research Council, and she is going to present a combination of field sampling and modeling with radiative transfer models.
Okay, good afternoon, everybody. Well, as Javi said, I'm Pilar Martin, and I will start telling that this is a collaborative work that Javi Pacheco and myself have coordinated from Max Planck and CSIC, but there is a lot of other contributions, either in the modeling or in the providing data for calibration or validation of the model. So, well, this is some summary of the presentation. I will start with a few of contents and objectives of this work. Then I will tell a few words about how we couple the pro-sail and the fly model to simulate this system. A small description of the field data that we have used, how we designed the lookup table for the estimation of the spectral characteristic of the ecosystem, and then how we validate the model at the different spatial scale, and just a few words about some preliminary analysis on predictive models. So, well, putting this work in context, this is part of a research project that is funded by the Spanish Ministry of Science, that is called Synergy, and the general objective of this project is to try to explore the synergies between medium resolution sensor, Landsat 8 and Sentinel-2 in order to better improve the monitoring of key biophysical and structural parameters in specifically in tree-grass ecosystems. So, as you can see here, basically the project was wanted to deal with two well-known 3D radiative transfer models, Flight and Dart, in order to simulate the spectral characteristic of the ecosystem, and then by combining the physical and the empirical approach to be able to derive three main biophysical and structural parameters that are canopy water content, leaf area index, and chlorophyll content. So in this part you will see the specific activity that I will talk about this afternoon. So in this case I will refer only to fly because we decided to start with fly. We thought it was easy. After some months working with fly, we realized that it was not the truth. So supposedly that will be also difficult, but flight it is. So we started with flight, and we coupled two different radiative transfer models, 1D pro-sail and 3D flight, in order to simulate the different vegetation layers in our ecosystem. So we use field biophysical data to parameterize the model and then to validate the data. We produce a simulated spectral library, and then we are using now this library to develop predictive model using a statistical method, higher spectral statistical method like partial least square regression and also vegetation indexes. Then we validate both the simulated spectral library by comparing with the spectral data acquired at ground level with field spectroscopy and airborne level and satellite. And then we validate the derived parameters by comparing with the biophysical parameters that are measured in the field. And as I said, our main focus is the tree-grass ecosystem, and you will say, why a tree-grass ecosystem? These people is crazy, because you have tree, grass, shadows, and in some cases you can also have shrub. So that's a very difficult problem from the remote sensing point of view. Nobody wants to work in tree-grass ecosystems. We did, and we have been working for more than 10 years in this ecosystem. We learned a lot about that, but we couldn't still answer all the scientific questions that we did at the beginning 10 years ago. But we're in the way. Well, this is a challenge ecosystem, but it's interesting to work with because it covers 1/4 of the Earth's surface in a different way by combining grass, shrubs, and trees in sparse trees. It's basically located in semi-arid climatic zones, which are quite vulnerable to climate change. They are, in some parts of the world, they are very related with livestock production and with pastoral subsistence. And as I said, it's a remote sensing challenge because we have vegetation with different dynamics, with different properties, with different functions. We have a strong geometrical component, and also in this semi-arid ecosystem, and especially in the Mediterranean area where we are working, we found that the optical properties of our vegetation is not properly represented in most relative transfer models. So this is a general scheme of how we couple the two models. As I said, we use 1D model, ProSail, in order to simulate the grass layer. In our ecosystem, we don't have shrubs. We have grass and trees. In our case, those trees are evergreen trees, but they have an annual renewal of part of the leaves of the crown. So there are a period during the year where you have in the tree crown the new leaves and the old leaves, and those have very different biophysical characteristics and also spectral characteristics. So this is the general scheme. So you will see in the right the ProSail inputs, and I will describe now quite quickly all the input data that we use to parameterize the ProSail model. Basically, we use spectral data and biophysical data through destructive sampling. And then for the trees, here in the part of the fly, we combine spectral data, biophysical parameter sample in the field, and also LiDAR data, airborne LiDAR data. So we have some common variables related with the illumination and observation conditions that we apply to both models. And then we combine the two by taking into account the diffuse and direct fraction of the radiation. So, as you know, when you are using empirical models, you need a very good field data in order to establish a robust relationship between the two set of variables that you want to put in common. So in this case, biophysical parameters and spectral data. But for the radiative transfer model, you also need very good data and complete set of data to properly parameterize the model. So in this case, we have an important database that we have been collected in a tree grass ecosystem in Spain. This is locally called the ESA. In Portugal, I think it's called Montado, and it's an ecosystem which is characterized by a grass layer, a combination of a grass and shrubs and sparse trees, and is used in Spain specifically for livestock production. So we have been sampling in this ecosystem for about 10 years, but for this project we have used the last data that we compiled from 2013 to now. We were in the field two weeks ago. For the grass layer, we are taking, every time we go to the field, we measure top of canopy field spectroscopy using an ASD field spec 3. And at the same time, in the same plots, we take destructive sampling in order to estimate chlorophyll and carotenoids content, dry matter content, and water content. And then also we, by scanning the samples, as you can see here, we calculate the leaf area index, both of the green and the dry fraction. So we have the total leaf area index and the green leaf area index. And for the trees, well, we have been we measured the bark of the tree using the field spec 3 attached to a plant probe. For the leaf of the trees, we have been using field spec 3 attached to a Lichens integration field to measure both reflectance and transmittance factors. And in the same leaves, we calculate the chlorophyll, carotenoids, dry matter, and water content. And for the crown characteristics, we have been measuring the leaf area index using a Lichens Light 2200 sensor. We derive the shape and dimension of the tree crowns using the airborne LiDAR, and we also measure the core fraction, that is the percentage of new and old leaves in the tree in the different phenological periods by manual counting. We also derive the tree fraction cover. In this ecosystem it's about 20%, but it changes depending on the area. And for that we use an orthophoto with a 25 centimeter resolution. And we measure this fraction cover trying to simulate a Landsat pixel. So we measure the fraction in its semi-Landsat 30 by 30 meter pixel. And for the soil, we have measured the spectral characteristic of our soil using the SD field spec 3, and then we extended this data set by model inversion using the BSN model included in the scope. So with all this data, we designed the lookup tables in order to derive the spectral, the spectra of the simulated spectra of our ecosystem. One of the main characteristics of our ecosystem is the temporal variability. We have a lot of spatial variability, especially in the grass, but we also have a lot of temporal variability because the grass has a very strong phenology. So in this case, we decided to reduce the lookup table size and range, dividing the lookup table in 4. So we define 4 what we call phenophases, and then derive a lookup table for each of these phenophases. And how did we decide about these phenophases? We analyzed a temporal series of 16 years of MODIS M-bar product, and then using TimeSat software, which is an open software produced by the University of Lund, we calculate the beginning and end of the season, and then the peak of the peak and the minimum of the NDVI each season. And with this, we get 4 different phenophases. The first one is we call the summer drought, so it's the period when the grass is completely dry and you only have the trees that are green because are evergreen trees. The autumn regrowth, when after the first rains, after the summer, the grass regrowth. So we have again grass green and the trees. Then we have the biomass peak, usually in the spring. And after that, when the temperature increases, we have what we call the greenness decay. So you have a mixture of green and dry grass that finally becomes some basically dry grass. Well, for each phenophase, we produce a lookup table, and we did it by using the lighting hypercube sampling. We include the process and flight parameters. You have the table there, but it's the list of parameters that I put in the first scheme. And in order to avoid non-realistic situations, we applied range based on the field data. So we consider the minimum and maximum range based on field data retrieved in each of the phenophases. And then we establish a linear relationship of all the variables in order to not only to avoid ranges that are out of our natural range, but also relationship between variables that are not real. So we established a linear relationship with leaf area index. Okay, I will go more quickly. Well, this is the evaluation. As I said, we evaluate the model by using spectral data measured with the field spectroradiometer for the grass layer, and then spectral data obtained from the airborne imager and satellite data. Well, you can see here in gray is the spectra that is produced using the lookup table, using the ProSail and Fly models. Well, this is ProSail, sorry. This is only ProSail, so we are here simulating only the grass layer, and the red spectra is the spectra that we measure in the field. As you can see, well, the range of the red spectra is reduced when compared with the simulated one, because we go to the field only in specific periods of the year, so we cannot have the whole range of the variation. But you can see that there is a good agreement, except in the phenophase 2 and in some cases in phenophase 1, and we relate this with the problem that we have in some Mediterranean ecosystem when there is a remnant, there is a combination in some periods of the year of green material with decomposed material, which is standing from the previous spring or summer in this case. So, well, this is an example of what I explained. We detect that in some cases, some properties were not well represented by the radiative transfer models. In this case, the standing disk material that you can see here, in what the effect that is producing in the spectral signal is a reduction of the near infrared, and this is not well represented by the radiative transfer model. Well, and this is the multi-scale evaluation using airborne and satellite data. For the airborne, we use CASI images. We have 4 overpaces to compare with the simulated data, and for the Sentinel-2, we use 3 overpaces. In this case, we simulate with ProSail and Fly these plots of 75 by 75 meters. In the general simulation, we were not considering a specific distribution of the trees, but in this case, we simulate the exact position of the trees in these plots that are real plots in the field. Well, and this is the for Sentinel. In this case, we use this image in February, but the problem here, you can see here that there are more differences when you compare with the simulated and the Sentinel data, because in this case, there was a difference of 22 days between the sample data and the Sentinel image. In those 2 images, in April and May 2017, the agreement between the simulated and the measured data is quite good. And well, this is a preliminary analysis of the predictive models. In this case, we are using a lookup table of 10,000 samples. We use 6,000 samples for training and 4,000 for validation. And the statistical technique is partial least square regression. And as you can see here, at least in this preliminary analysis, the estimation is quite good with relative error that are acceptable and with good R2. And well, as a conclusion, the top of canopy reflectance factors and the biophysical parameters that has been scaled from individual vegetation layers, in this case the grass and the trees, to ecosystem scale has worked properly. ProSail and Fly allows to represent the optical properties of a tree grass ecosystem. The evaluation of the uncertainties using information from different scales, from field to satellite, has shown that there is a large complexity, and the mismatch between the simulated and the measured data is larger at when we go from the ground scale to the satellite scale. We need to evaluate the problems that some radiative transfer models have to simulate Mediterranean vegetation. And finally, with this preliminary analysis, we found a successful prediction of the canopy parameters using partial least square regression. And finally, MAPI told us about including some connection with other working groups and potential short-time scientific missions. And regarding the connection with other working groups, well, I can see here the connection with the time series analysis for the design of the lookup table, the calibration and validation of data and protocols for assessing the time series, with working group 3, the sensor synergy, the use of airborne temporal series of optical and thermal data. We have a series of this data in Majadas from 2009. And for working group 4, we have the possibility of interacting with protocols and uncertainties propagation for the evaluation of the satellite products. And regarding the short-term scientific mission proposal, well, I didn't include nothing specific here, but we are willing to receive people wanting to work with upscaling issues, specifically in this tree-grass ecosystem, with estimation of biophysical parameters, and with 3D radiative transfer models. As I said at the beginning, we are starting to work in dark now in order to compare the performance of the two models in this specific ecosystem. And I think, yeah, that's all. Well, the more details about the work that I have been trying to summarize here and in this publication it was published recently in Remote Sensing. So if you want more details on this, yeah, you can have a look to this paper.
Okay, we're a bit tight, but maybe we have time for one question.
Thank you very much for the presentation. I have one question regarding the measurement you did in the field for the leaf area. And then you said that you have measured the leaf area in order to calculate the leaf area index. Okay, so what is the size of the area you consider in the field to collect these grasses?
We collect the grasses with the destructive sampling in 25 by 25 centimeter plots.
Okay, so in these 25 centimeters, you collect the leaf area?
We collect all the grass that is included in that square, and then we, in the laboratory, we select a subsample of that whole sample, and then we calculate all the variables using that subsample.
And then how do you then make a distinction? I mean, because within that 25 centimeter, I suppose you also have dry material.
Yeah.
So you part of that 25 by 25 is already gone because it's dry vegetation. And then you have a portion which is left by, and then within that portion you still take subsamples.
Yeah, in the subsample includes the dry and the green fractions. Then we manually separate the grass and the green and the dry fractions, and we process separately the two subsamples.
Because you mentioned that there is a large spatial variability in the grasslands, so I would like to see how these 25 by 25 centimeters can actually represent the area.
Yeah, that's the very important question here. In this case, we are sampling 33 plots every time we go to the field. So these 25 by 25 centimeters are 33. The problem is that our reference plot is a 25 by 25 meter plot, and then in each of 25 by 25 meter plots, we usually sample 2 or 3 small squares of 25 by 25 centimeters. So what we find out is that these 3 are not well representative of the 25 by 25 meter plot, but the 33 we are measuring in all the area is enough representative of the variability between in that area. So when you go to the small, to the very high resolution, you see that there is a strong variability. So you will need to sample every meter, more or less.
We can discuss after
Yeah.
the presentation.
Yeah, maybe we can, because we need to continue. We have the last presenter today, which is Sebastian, I think. And yeah, thanks, Pilar. And let's move on with the.
So yes, thank you very much. My name is Sebastian Wienecke. I'm at the moment working at the University of Antwerp. And I would like to talk now about sun-induced fluorescence yield under plant stress. And maybe like one sentence to give like why sun-induced fluorescence so interesting. So it was briefly mentioned in the beginning of the workshop. The nice thing about sun-induced fluorescence is that it's directly or more directly related to the plant physiology instead of the reflectance, which is mainly like based on the greenness or the chlorophyll content. So the big hope about sun-induced fluorescence is actually that we can really like access the light reactions of the photosynthetic process. And this is also where I'm mainly interested in my work. So to give a short background about me and my research interest and how this fits actually in the working group 1. So I started my PhD in the question, how can we relate sun-induced fluorescence to estimate GBP? And I worked with a new airborne sensor, which is called HiPlant. And we tried to actually relate sun-induced fluorescence to GBP in different methodologies. And as maybe the people who work with sun-induced fluorescence, there's a strong linear relationship between these 2 parameters. So, but while working with this, the difficulty is that there's like a lot of covariation between sun-induced fluorescence and GBP. So it was actually, and the problem with airborne measurements is that you only have like certain kinds of overflights. So if you want to really get like a bigger picture about fluorescence over a season, this is very difficult to do with airborne measurements. So the next part of my work, I went to the field and we measured for a longer time period sun-induced fluorescence and particular fluorescence yield and compared this to the lightest efficiency, because this is actually like one step closer to the physiology of the plant. And yeah, and now, like in Antwerp, I started to actually work on the leaf because we have a lot of difficulties also in the field to really get to the physiology when we measure fluorescence on the canopy. I will go into this like a little bit more in detail in course of the talk. So at the moment, this year we have a measurement campaign. And there I want to try to now go back, so from the leaf to measure fluorescence at the same time on the canopy, and then to see like, okay, in the long run, can we actually going back to the like drones or airborne measurements or maybe even satellite. So now in particular I want to talk about the measurements we did in 2015 of a sugar beet. We measured with the hyperspectrometer system, which has a spectral resolution of 1 nanometer, and we treat sun-induced fluorescence in the red and far-red absorption band with the IFLD method. So we had a very quick acquisition time of 6 seconds, so which allowed us to collect a lot of data samples. And the system was located close to an eddy currents tower, and we measured over 3 months continuously. and during the 2015 heat wave. So first, like, why the relationship between fluorescence and GPP is actually like a little bit difficult to interpret at a certain point. So a lot of papers state that actually GPP has a linear relationship, or fluorescence has a linear relationship to GPP, and this is true if the plant is unstressed. But as soon as the plant is stressed, and with the stress the canopy changes, or like the leaf is rolling or wilting or has like other effects, this relationship breaks down. For the fluorescence at 760 nanometer, and in particular for the fluorescence 687 nanometers, which is also to reabsorption effects. And second, this strong relationship between fluorescence and GPP is actually driven by APAR. So in particular for the sugar beet, we see that fluorescence has a much stronger relationship to APAR than to GPP. So a lot of change we actually see, or like a lot of these linear relationships depend on APAR. So what we did then is to actually compare the APAR relative fluorescence at 760 meters, that's the fluorescence yield, and with the GPP APAR relative lightness efficiency. And what we can see is that over the full season we actually see like a logarithmic increase, but if we only look at, which is mainly driven by the different response to the drought and to the unstressed. So if we only look into the drought stress data or the unstressed data, the relationship is much weaker. So then I have to say, to this data set, so this is a 30-minute average, and we already cleared this relationship a lot because we only choose clear sky days, because under cloudy conditions, this relationship, you get a lot of retrieval errors, and we choose only data with a solar zenith angle below 60 degrees. So if you would not do that, you actually see a cloud of points. And this is also what you can see like in a lot of publications, that if you clean the data with the solar zenith angle, you get like a clearer relationship, but still it's like pretty difficult to interpret. So I compare this with some data in the internet. So this is based on GOMI2 data. So the fluorescence yield to the lightness efficiency for different plant functional types. And you see that the relationships seem to be like very similar, or at least that we have like a positive increase between fluorescence yield and lightness efficiency. And that's actually strange, because this is not what we would expect. Because from measurements on the leaf, we would expect that under unstressed conditions, the fluorescence has a negative relationship with the photosynthetic, so with photochemical quenching. And with increasing stress, or with increasing non-photochemical quenching, this relationship is then changing to the positive. And then under extreme stress conditions, we have an increase, or like a negative relationship again. And this we cannot really see in our data. So what I then checked is for certain kind of covariations between other vegetation indices, and I saw that that's actually structural, and the structural index MTVI still has a very high relationship to the fluorescence yield. So we calculate the residual and then tried to see how the residual is actually behaving to the lightness efficiency. And we see that we can invert these relationships, but still I don't think if this is really makes sense. So I would be very careful in the interpretation here. So actually the blue ones look nice, but the red ones should be actually now like in this behavior. So I would be careful in interpreting this, but this was also the point where I realized to really have an idea about what is it what or about the physiology of the plant we really have to measure on the leaf at the same time as we measure on the canopy. So like a short summary for the canopy fluorescence yield. So the relation between fluorescence yield and light use efficiency changes with the light conditions, with the solar zenith angle, with stress-related structural changes of the canopy. So if the leaf is really the leaf is rolling, folding, or if the chloroplast move to the lower part of the leaf. It depends on the chlorophyll content, because the reabsorption effects will be less strong if the chlorophyll content decrease. And last but not least, also the plant physiology really plays a role. But to really come to this point where you can relate fluorescence yield to the plant physiology on a canopy, this is still a challenge. So now I would like to talk about like an experiment we did in 2 years ago. It was a phosphorus manipulation experiment in Antwerp, where we had different phosphorus treatments. From P4 has like the highest phosphorus treatment, P1 the lowest one, and then 2 of these treatments were also like with sterilized soil, so no mycorrhiza was available for the plant. So during the growing season for the maize, we had 2 measurement campaigns, and we measured the gas exchange, active fluorescence, passive fluorescence, and leaf pigment, the leaf pigments, and we had around 104 leaf samples. And the hypothesis is so the phosphorus limitation actually inhibits the ATP synthase, which leads to a lumen acidification, which increases the non-photochemical quenching, or which triggers the non-photochemical quenching, which has then which then reduces the electron transport rate. And the reduction of the electron transport rate has then also an effect on the fluorescence signal. At the end of the campaign, we measured destructively the biomass, and what you can see is that actually the phosphorus treatment has a strong effect on how much biomass was accumulated. So for the treatments with the lowest phosphorus, we have like very similar values, while the treatments which were affected or which had no mycorrhiza, the plant with the lowest phosphorus availability and no mycorrhiza was actually dying in the end. So we also analyzed the biomass distribution, and what you can see here is that for P1 and P2, the plant actually invested a lot of biomass or more biomass into the root system. So to actually access more phosphorus and nutrients. So what we see in the end of the campaign is actually that the leaf and P ratio was balancing out for these treatments, but not for the treatments without mycorrhiza. So in campaign 1 we measured the electron transport rate, and you can also see here that the P limitation has had a strong effect on the electron transport rate. So the electron transport rate was going down a lot, and in campaign 2 the electron transport rate really was like nearly at the same level for the P limitation, also for the P1, P2, P3 and P4, so for all different treatments on the phosphorus. But not for the treatments who had no mycorrhiza, because they were not able to really assess or access more phosphorus from the soil. So in the next step, I compared then the fluorescence yield to the electron transport rate on the leaf, and we can see that we have like a linear increase for all the treatments which had a positive relation, which were which were like in unstressed conditions. And the size of the points indicates how strong the photochemical reflectance index was, which is linked to the xanthophyll activity. So if the dot is bigger, the xanthophyll activity is stronger, and we would expect higher stress values. So for the treatments which were under the strongest stress, we saw that actually this relationship now changed. So, and for the two dot points where the plants were under severe stress, this relationship was going up, and I expect that the last dot there suffered under extreme conditions, which is, yeah. So, and then if we compare this to what we would actually expect from active fluorescence measurements, we can see the same pattern. So this gives me some confidence about actually the fluorescence signal after measuring it a lot on a canopy and always hoping like, oh, is it really, can we really get information about the physiology? So yes, I think we can. But still, we have there's a lot of steps to do, and I actually hope that with a lot of people collaborating, we can come closer to the solution to really, to really get rid of the canopy effects. So yeah, like a short summary. Cyanide fluorescence is a good estimator for GPP under non-stress conditions, but it's mainly related to APA. So if you're just interested in a good GPP product, sunny fluorescence is actually like this. All the sunny fluorescence products seem to be actually very good. But if you want to go to the physiology of the plant, you have to be very careful in interpreting the signal. So similar things are true for the fluorescence yield, because they still affected by a lot of factors. I will not name them all again. But as I said, on a leaf we can actually track the photosynthetic light reactions. So yeah. So the question is just how can we account for the structural influence of the canopy, and one way I just put here is to estimate the escape probability of sun-induced fluorescence. If we do this by models, or if it's possible to do this with other remote sensing proxies, this is the biggest challenge I think at the moment. Then I would like to say something about a short scientific mission. So as I said in the beginning, in 2019 I will start this year I will start my experiment, and we want to measure, or we will measure on potatoes under drought conditions and nutrient limitations. So I want to measure the gas exchange of the canopy, the biomass, the soil water content, and a lot of other stuff. You can see this here. And actually the most interesting part will be to really compare leaf fluorescence with canopy fluorescence, and can we see really these patterns from the leaf to the canopy to better understand what is really going on. So the questions I actually want to address during this time, so if someone thinks I have a nice idea and I could join this experiment, or could help out or whatever, I'm very happy if someone is interested in it. Also for modelers, because one of the objectives is also that I hope I can do a 3D reconstruction of one of the potatoes, and then really calculate with Dart the escape probability. I do not have experience with Dart, so I'm very happy if someone shows up and says yeah, that sounds really interesting. And then to really model the best escape or the best product of escape probability, and then compare it to reflectance data. Yes. So.
Thank you, Sebastian, for a very nice presentation. Is there any questions for Sebastian?
I want to. So you were showing this plot, the size of the points were related to the PRI. But PRI also, I mean, it's not only dependent on MPQ, but also it depends on the kind of pigment pool. So do you know how normalize the PRI you were measuring by pigment pool?
So I did not go into this because I concentrate on fluorescence of the fluorescence yield. But actually, one part of this work is also to correct the PRI for the pigment pool. So this is what I did, that I actually related it to the sample for pigments. So it's like, and it shows like a linear relationship to the electron transport rate.
Okay, good, thanks.
Okay, I think we're done. Okay, I think that brings us to the end of our first day. Maybe we can give a final applause to all those who were there. So final thing I want to say, so in order to start tomorrow in time at 9 o'clock, I'd like to ask the Group 2 chair, there's this number to you here so far, I don't know, Helge is also here, meanwhile, hi. Please make sure that the presenters have uploaded before 9 o'clock, so maybe you can now fix it. Santiago, Helge, Lammert, and